Right now, as you look up at the night sky, something vast and enigmatic is drifting just beyond the edge of human vision, our closest galactic neighbor, the Andromeda Galaxy. It hangs there, a faint smudge of light 2.5 million light-years away, a spiral of stars so immense it defies comprehension. For centuries, we've observed it with wonder, studied its structure, and dreamed of what secrets it might hold. But what if I told you that some of its greatest mysteries aren't hiding in its bright, bustling core, but drifting silently in the darkness all around it? Welcome to the halo of Andromeda, a sprawling, invisible ocean of dark matter, ancient stars, and strange, wandering objects that tell a story far stranger than we ever imagined. Today, we're setting out on a journey into that deep and lonely frontier, a place where the rules of physics seem to twist and where cosmic oddities lurk in the shadows. Scientists have long known that galaxies like Andromeda are surrounded by vast halos regions that extend far beyond their visible disks. But it's only recently, with the power of advanced telescopes and patient observation, that we've begun to uncover what's really out there. Not just dim stars or faint clusters, but 30 truly bizarre objects, each one stranger than the last. Some of them shouldn't exist, others defy classification. And a few might just rewrite what we thought we knew about how galaxies form and evolve. So what are these enigmas? They range from orphaned star clusters hurtling through the darkness alone, to rogue planets drifting untethered from any sun, to structures so unusual that astronomers still debate what they're even looking at. Each one is a clue, a piece of a puzzle that stretches across billions of years of cosmic history. And as we explore them together, you'll begin to see Andromeda not as a distant island of stars, but as a living, evolving galaxy with a hidden story waiting to be told, a story that, in many ways, is also our own. So settle in. Where we're going, you're going to need a sense of wonder. Our first stop on this tour of cosmic oddities brings us to a structure of such immense scale and subtlety that it was completely hidden from us until modern astronomy peeled back the layers of the night sky. This is the Andromeda Giant stream, a vast river of stars flowing through the galaxy's halo. To call it a stream is almost an understatement. It's more of a colossal stellar highway, a ribbon of ancient suns stretching across hundreds of thousands of light-years. Its discovery wasn't the result of a single eureka, a moment, but a patient, meticulous piecing together of data from powerful telescope surveys. Astronomers were mapping the faint, outer regions of Andromeda when they began to notice an unexpected overdensity of stars, a faint but distinct current flowing against the darkness. This wasn't a tight, spherical cluster of stars, but something far more elongated and diffuse, a ghostly signature written in starlight. The stars that make up this stream are truly ancient, some of the oldest in the entire local group of galaxies. They are population 2 stars, a classification for stars that are metal-poor, meaning they formed from the pristine hydrogen and helium that existed in the very early universe, long before successive generations of stars had forged heavier elements in their cores and scattered them across space in supernova explosions. Studying the composition and motion of these stellar fossils is like reading a history book that dates back to the dawn of cosmic time. But how did such a vast structure, this river of ancient suns, come to be? The prevailing theory is as dramatic as it is destructive. Astronomers believe the giant stream is the stellar corpse of a dwarf galaxy that strayed too close to Andromeda billions of years ago. In a violent and drawn-out process, the immense gravitational tides of the larger galaxy would have begun to shred the smaller one, pulling it apart over the course of eons. Visual simulations of this cosmic demolition are both beautiful and terrifying. We see the dwarf galaxy, a small cluster of stars, making its initial approach. With each pass, Andromeda's gravity acts like a powerful hand, stretching and distorting the smaller galaxy, plucking stars from its grasp and flinging them into elongated orbits. Over time, the dwarf galaxy is completely dismembered, its stars no longer a cohesive family, but instead strung out into this immense, looping river that now forever circles its destroyer. The giant stream is therefore a fossil record of a galactic merger, a permanent monument to a violent event that took place when our own planet was still a molten rock. It's a stunning reminder that galaxies are not static islands but dynamic, evolving entities that grow by consuming their smaller neighbors, and their halos are the archives where the evidence of this cosmic archaeology is preserved. But if the giant stream represents the ghost of a devoured galaxy, our next object is a pristine survivor from the universe's infancy, a relic so pure it forces us to question our most fundamental theories of star formation. Drifting in the halo, roughly 65,000 light-years from Andromeda's center, is the enigmatic globular cluster known as EXT8. At first glance, in images from the Hubble Space Telescope, it looks like many other globular clusters, a breathtaking, dense sphere of hundreds of thousands of stars, a glittering swarm of suns held together by their mutual gravity. But what makes EXT8 extraordinary isn't its appearance, but its chemical makeup. This cluster possesses an almost impossibly low metal content, a term astronomers use for any element heavier than hydrogen or helium. The stars within EXT8 are metal poor to a degree that defied all existing models. When it was measured, its metal content was found to be a mere 0.0008% of that found in our Sun, making it the most metal-deficient globular cluster ever discovered in any galaxy. This extreme poverty of heavy elements is a hallmark of incredible age. It tells us that the stars in EXT8 formed from a cloud of primordial gas that had never been enriched by the ashes of earlier stellar generations. They are first-generation stars in a very real sense, blazing into life when the cosmos was still young and pristine. Their existence pushes the estimated age of this cluster to nearly the age of the universe itself, around 13 billion years old. This presents a profound challenge to astronomers. Our prevailing theories suggested that to form a gravitationally bound cluster of this immense size and density, you needed a certain amount of heavier elements to help the initial gas cloud cool and condense efficiently. EXT8, with its near-total lack of these metals, simply shouldn't have been able to form into such a massive, cohesive object. Its very existence is a paradox, a cosmic rule breaker that forces us to reconsider the physics of how the very first structures in the universe coalesced out of the darkness. Studying EXT8 is like finding a perfectly preserved fossil that contradicts our entire timeline of evolution. It suggests that the early universe was far more capable and efficient at building massive, complex structures than we ever dreamed, operating under physical conditions we are only beginning to understand. This single cluster, a tiny speck in Andromeda's vast halo, holds the key to rewriting a chapter in the story of cosmic dawn, proving that even the oldest objects in the sky still have the power to surprise us. Yet for all its ancient light, the halo holds a mystery that emits no light at all, a presence known only by the ghostly hand of gravity. Our journey now takes us to one of the most perplexing discoveries in Andromeda's halo, an enormous, isolated clump of dark matter. This isn't an object you can see with any telescope because it doesn't consist of stars, gas, or planets. It is quite literally nothing, and yet it has immense weight and presence. Astronomers only found it because of a phenomenon called gravitational lensing, one of the most elegant and powerful tools in modern astrophysics. The theory, first predicted by Einstein, tells us that a massive object will warp the very fabric of space-time around it. Think of placing a heavy bowling ball in the center of a taut rubber sheet. It creates a deep well. Now, if you roll a marble past it, the marble's path will bend following the curve. In space, the marble is a beam of light from a distant galaxy. This is precisely how the dark matter clump was detected. As light from galaxies far beyond Andromeda traveled across the universe toward our telescopes, it passed through Andromeda's halo. In one specific region, astronomers meticulously measured how that distant light was subtly bent and distorted. The pattern of distortion revealed the signature of a tremendous amount of mass concentrated in a specific area, a gravitational well deep enough to twist the path of light. But when they pointed every available instrument at that spot, optical, infrared, X-ray, they saw absolutely nothing. No stars, no gas clouds, no detectable source for this immense gravitational pull. They had found a ghost, a huge and isolated concentration of invisible mass, a clump of pure dark matter just floating in the galactic hinterlands. This isolation is what makes the discovery so deeply puzzling. According to our standard models of cosmology, dark matter is the invisible scaffolding upon which all visible structures are built. We expect to find it in vast, diffuse clouds enveloping galaxies or concentrated in the centers of galaxy clusters. But finding a dense, isolated knot of it just sitting alone in the emptiness of the halo is like finding a single, perfectly formed brick just lying in a field, miles away from any ruins or construction site. It shouldn't be there on its own. The leading theory suggests it could be the remnant core of a small, ancient galaxy that was torn apart by Andromeda's gravity billions of years ago. Just as the giant stream is the visible starry debris of such a collision, this dark matter clump could be the invisible heart of that devoured galaxy, the dense dark matter halo that once held it together, now left to drift alone after all its stars were stripped away. This solitary phantom mass offers a potential key to unlocking the true nature of dark matter itself. Its very existence and stability over billions of years could help scientists figure out what this mysterious substance is actually made of. For instance, if dark matter particles are cold, meaning they move relatively slowly, they would more easily clump together into such dense, stable structures. If they are warm or faster moving, such tight clumps would have difficulty forming and would instead smear out into smoother distributions. By studying the size and distribution of these isolated clumps, astronomers can effectively run a diagnostic test on the universe's most elusive material. This invisible knot in Andromeda's halo is therefore more than just a curiosity. It is a natural laboratory, a cosmic proving ground for theories that seek to explain the 85% of matter in the universe that we cannot see. Moving even deeper into the shadows of the halo, we encounter a class of object so faint and diffuse that it pushes the very limits of what we can call a galaxy. This is an ultra-faint dwarf galaxy, a ghostly congregation of stars so sparse that for decades it remained completely invisible to us, hidden within the vast expanse of Andromeda's outer reach. Its discovery wasn't about spotting a bright smudge in a telescope eyepiece. It was a triumph of statistical astronomy and patient digital sleuthing. Astronomers used some of the world's most powerful telescopes to take incredibly deep, wide-field images of the sky around Andromeda. They weren't looking for a glowing object, but rather for a subtle, consistent overdensity of individual pinpricks of light. They meticulously counted stars across these enormous celestial maps, and in one particular region, they noticed a statistically significant grouping of very old, very faint stars that stood out against the random background. It was like identifying a faint, shimmering pattern in a vast field of falling snow. This wasn't a tightly bound cluster, but a sprawling, gravitationally connected system, and it was officially designated as a satellite galaxy of Andromeda, albeit one of the most feeble ever found. Its total luminosity is astonishingly low. This entire galaxy, spanning perhaps 1,000 light-years, gives off less light than a single, average bright star within our own galaxy. In a truly dark sky, away from city lights, your eye can easily see a single star like Polaris from hundreds of light-years away. Yet this whole galaxy of thousands of stars is too dim to perceive without immense technological aid. This profound dimness is its most defining feature. The stars within it are primarily ancient, metal-poor red giants and main sequence stars, stars that burn their fuel slowly and emit a pale, cool light. There is very little free floating gas or dust left to form new, brighter stars. This is a galaxy that lived its life quickly in the early universe and has been fading quietly ever since. Its ghostly nature makes it a crucial missing link in our understanding of galaxy formation. Cosmological models have long predicted that large galaxies like Andromeda and our Milky Way should be surrounded by hundreds of such small dwarf galaxies, the leftover building blocks from which the major galaxies assembled billions of years ago. Yet for years we could only find a few dozen, creating a glaring discrepancy between theory and observation known as the missing satellites problem. The discovery of ultra-faint dwarfs like this one in Andromeda's halo is a direct solution to that problem. They were never truly missing, they were just hiding in plain sight, too dim for previous generations of telescopes to see. Each one of these faint smudges is a pristine time capsule from the universe's formative years. Because they have experienced so few interactions and have such simple gravitational histories, they represent some of the most dark matter-dominated objects in existence. This makes them perfect natural laboratories for studying the properties of dark matter itself. By observing the motions of their few visible stars, astronomers can map out the distribution of the invisible dark matter that must be holding them together. So, while it may be one of the least impressive objects to look at, this ultra-faint dwarf galaxy is arguably one of the most significant. It's a fossil from the dawn of time, a key that helps unlock the mystery of the invisible cosmic web, and a direct piece of evidence showing us how the largest structures in the universe were built from the smallest, faintest beginnings. But not all denizens of the halo are ancient stars or invisible matter. Some are vast, silent clouds of raw material, the primordial fuel for creation itself. Drifting through the darkness is a colossal reservoir of hydrogen gas, a structure so immense it defies easy explanation. This isn't the warm, dense gas found inside galactic disks where stars are actively being born. This cloud is cold, diffuse, and isolated, a ghostly island of potential detected not by optical telescopes, but by the faint whisper of radio waves it emits into the cosmos. Its discovery came from painstaking observations by radio telescopes like the Very Large Array, which can tune into the specific frequency emitted by neutral hydrogen atoms as their electrons change spin states. This signature, known as the 21-centimeter line, acts as a cosmic beacon, allowing astronomers to map the distribution of this fundamental gas even in the deepest, darkest voids of intergalactic space. The sheer scale of this cloud is breathtaking, containing enough raw hydrogen to form millions of suns like our own. Yet it hangs in a state of suspended animation, a vast nebula frozen in time. The central mystery is its origin story. How did such a massive collection of gas end up so alone, so far from the bustling star forming regions of Andromeda's main disk? Astronomers are investigating two compelling and opposing theories. The first suggests an explosive internal origin. Galactic outflows driven by the ferocious winds from supernova explosions or the intense radiation from bursts of star formation could have violently ejected this gas from Andromeda's disk billions of years ago. In this scenario, the cloud is a cosmic belch, a blast of material vomited out into the halo where it has been drifting and cooling ever since. The second theory proposes an external, gentle accretion. It's possible this cloud is not an exile, but a newcomer, a pristine strand of the intergalactic medium slowly falling into Andromeda's gravitational embrace. This would make it a remnant of the cosmic web, the filamentary structure of gas and dark matter that connects all galaxies in the universe. In this view, the cloud is a late arrival of the very same raw material that first built the galaxy, a delayed delivery of cosmic building supplies. Spectral data offers clues, as the precise velocity and subtle motions of the gas can hint at its history. gas that was violently ejected would show different kinematic signatures than gas that is serenely falling in for the first time. Its future is as uncertain as its past. Could this vast reservoir ever coalesce and ignite into a new generation of stars? The conditions currently seem too hostile. The cloud is too diffuse and the pressure too low for gravity to overcome and begin the process of collapse. It lacks the heavy elements, the cosmic dust, that typically act as catalysts for star formation by helping gas clouds cool efficiently. However, if this cloud were to ever collide with another stream of gas or be compressed by a shock wave from some distant cataclysm, it could potentially trigger a spectacular, if isolated, burst of stellar birth. It would be a profoundly strange event, a flash of new light in the ancient darkness of the halo, a stellar nursery born far from the nurturing light of the galactic center. For now, it remains a sleeping giant, a reminder that the potential for creation, even when dormant, is never truly gone from the universe. Now, shifting our focus from vast, ethereal clouds to a tightly bound family of stars in a desperate rush, we encounter a stellar system that seems to be trying to escape the galaxy entirely. This is a high-velocity globular cluster, a dense sphere of hundreds of thousands of stars that is racing through the halo at a speed that defies easy explanation. Its motion is so profoundly fast that it stands out starkly against the more sedate drift of its neighboring clusters. Tracking its path requires precise measurements taken over years, even decades, and when astronomers finally plotted its course, they saw it wasn't on a gentle orbit. This cluster is on a high-energy trajectory, a celestial bullet that seems to have been fired from a cosmic cannon. Its velocity so great that it challenges the gravitational hold of the galaxy itself. How does something so massive attain such incredible speed? Astronomers are investigating two primary and equally dramatic origin stories. The first involves a violent ejection from the galactic disk. Imagine the dense, chaotic environment at the heart of a young galaxy, with stars being flung around by complex gravitational interactions. It's possible this cluster once orbited much closer to Andromeda's center. There, it may have had a close encounter with the supermassive black hole that lurks there. The immense gravitational forces at play could have acted like a cosmic slingshot, flinging the cluster out into the halo on a new, high-velocity trajectory. In this scenario, the cluster is a refugee, violently exiled from the crowded inner city of the galaxy to the sparse outer suburbs. The second compelling theory suggests this cluster isn't a native of Andromeda at all, but a captured interloper. It could have once been the central jewel of a small, dwarf galaxy that ventured too close to Andromeda. As the larger galaxy's gravity tore the dwarf galaxy apart, stripping away its stars and dark matter, this robust, tightly bound cluster could have survived the demolition. The energy from that galactic demolition derby would then have been transferred to the cluster, sending it careening on its new, high-speed path through the halo. In this case, it's not an exile but a survivor of a cosmic catastrophe, a trophy from a galactic conquest that now races through the victor's domain. To visualize this, motion simulations are crucial. They don't show a simple elliptical orbit. Instead, they reveal a sharp, open arc, a trajectory that suggests this cluster is either on a very long, stretched-out orbit that will take billions of years to complete, or it might even be on a parabolic escape route, destined to eventually leave the galaxy's gravitational influence altogether and become a true wanderer in the intergalactic void. Velocity charts further illustrate the anomaly, plotting its radial velocity, how fast it's moving towards or away from us, and its proper motion, its movement across the sky. The combined data point to a three-dimensional velocity vector that is simply off the charts compared to typical halo objects. This isn't just a curious oddity, it's a crucial test for our dynamical models of how galaxies work. The movement of every object within a galaxy is governed by the combined gravitational pull of all the visible matter. stars, gas, and dust, as well as the vast, invisible halo of dark matter. By mapping the predicted gravitational field of Andromeda and then watching how this cluster utterly defies those predictions, astronomers get to stress test their models. The cluster's extreme speed acts as a probe, revealing the shape and depth of the gravitational wells within the halo. If our models can't account for its motion, it means we are missing something fundamental, perhaps about the distribution of dark matter or the historical interactions that have shaped the galaxy's gravitational landscape. This one speeding cluster, therefore, is more than a spectacle. It's a key diagnostic tool, helping us to map the invisible forces that sculpt the entire galaxy. Deep within the halo, far from the brilliant spiral arms, we find a different kind of relic, not a single object, but a scattered population of ancient suns known collectively as the metal-poor stars. These aren't clustered together like a globular cluster. They are solitary wanderers, a sparse demographic of the halo's oldest inhabitants. Their defining characteristic is written in their light, revealed only when we break it apart into a spectrum. When astronomers point their most powerful spectrographs at these faint points of light, they don't see the strong, dark absorption lines for elements like iron, carbon, or oxygen that are so prominent in the spectrum of our own sun. Instead, their spectra are almost pristine, dominated by the broad lines of hydrogen and helium with only the faintest whisper of anything heavier. This extreme lack of metals, the astronomers' term for any element heavier than helium, is their badge of honor, a certificate of their profound age. To understand why this is so significant, we need to rewind the cosmic clock to the very beginning. In the immediate aftermath of the Big Bang, the universe contained only the three lightest elements: hydrogen, helium, and a trace amount of lithium. There was no carbon for life, no oxygen for water, no iron for planetary cores. The first generation of stars, often called population 3 stars, had to form from this pure primordial soup. These stars were behemoths, many times more massive than our Sun, and they lived fast and died violent deaths in colossal supernova explosions. It was within the furnaces of their cores and in the fury of their deaths that the first heavy elements were forged and then scattered across space, seeding the cosmic gas clouds with the raw materials for everything that would follow. The metal-poor stars we see in Andromeda's halo are the direct descendants of that first generation. They are second-generation stars known as population 2. They formed from gas clouds that had been lightly enriched by just one or two of those first supernova. Their incredibly low metallicity is a frozen record of the conditions in the very early universe, a snapshot of a time before countless stellar generations had polluted the cosmos with heavier elements. Each one is a time capsule, and by studying their composition, astronomers can perform a kind of cosmic archaeology, reverse engineering the properties of those very first unseen stars that lit up the cosmic dark ages. But these stars are more than just ancient relics. They are traces of Andromeda's deepest history. Their motion tells a story of violent beginnings. Unlike the stars in the orderly, rotating disk, these halo stars have chaotic, randomly oriented orbits. They plunge around the galaxy on wildly eccentric paths, some swinging extremely close to the center while others loop out to the halo's farthest reaches. This orbital ballet is a ghostly echo of the galaxy's violent assembly. The prevailing theory of galaxy formation, the hierarchical model, tells us that large galaxies like Andromeda were built over billions of years by consuming smaller dwarf galaxies. The metal-poor stars are the survivors of that carnage. They are the original stars from those devoured dwarf galaxies, stripped from their parent systems and scattered throughout the halo during the gravitational turmoil of merger events. Visualizing this with spectroscopic data is key to understanding. Imagine a graph on screen, a horizontal axis showing metallicity from low to high, and a vertical axis showing the orbital eccentricity of the stars. The data points wouldn't be a random scatter. Instead, they would reveal a striking trend. The stars with the very lowest metallicities, the true ancient ones, almost exclusively have the most extreme, highly eccentric orbits. This correlation is the smoking gun. It directly links a star's ancient composition to its chaotic path, proving that both are the result of a violent origin story billions of years in the past. These stars are the living evidence of Andromeda's aggressive growth, the celestial equivalent of finding scattered pottery shards from a long-destroyed ancient civilization, each one helping to piece together the story of how a mighty empire was built. While individual objects like star streams and rogue clusters tell specific stories, the grandest narrative of all is written across the entirety of Andromeda's extended stellar halo. This is the galaxy's final frontier, a spherical cloud of stars that stretches over 1,000,000 light-years from the center, a volume of space so immense it's almost impossible to visualize. For a long time, this region was largely theoretical. We knew it must be there, but mapping its faint, sparse stars was beyond our technical capabilities. That all changed with ambitious, multi-year sky surveys like the Pan-Andromeda Archaeological Survey, or P&AS for short. Using the powerful Canada-France-Hawaii telescope, astronomers didn't just take a picture of Andromeda. They patiently assembled a gigantic mosaic, a billion-pixel deep-field portrait that methodically charted the positions and colors of millions of individual stars in and around the galaxy. The resulting map is nothing short of revolutionary. It doesn't show a smooth, symmetrical sphere of starlight as some early models predicted. Instead, it reveals a halo that is profoundly lumpy, complex, and richly structured. It looks less like a clean, fuzzy bubble and more like a ball of yarn that has been tangled and twisted by a cat, crisscrossed with stellar streams, dotted with overdensities, and punctuated by vast, empty voids. This messy, intricate architecture is the undeniable signature of a violent and ongoing history of galactic cannibalism. Every loop, every clump, every faint river of stars is a fossilized remnant of a smaller galaxy that was consumed. The halo is not a pristine structure, it is a galactic graveyard, and the P&AS survey provided us with the first complete census of its inhabitants and their arrangement. This allows for a direct and fascinating comparison to our own home galaxy. The Milky Way also has a stellar halo, and we've been mapping it with missions like the Gaia Space Observatory. The difference between the two is stark and revealing. Andromeda's halo is significantly larger, more massive, and appears far more structured and disturbed than our own. Our galaxy's halo has notable features like the Gaia Enceladus stream from a major past merger, but it seems almost sedate compared to the sprawling, chaotic web of debris surrounding Andromeda. This tells us that while both galaxies have grown by consuming smaller neighbors, Andromeda has been the more voracious and aggressive predator, having ingested more and larger dwarf galaxies throughout its history. Three-dimensional modeling brings this story to life. By measuring the distances to these faint halo stars, astronomers can transform that flat, two-dimensional map into a stunning depth map, a three-dimensional point cloud of Andromeda's complete stellar population. Spinning this model reveals the true geometry of the carnage. We can see how some streams wrap around the galaxy, while others plunge directly through it. We can identify distinct families of stars that all share a common motion and origin, tagging them as the former citizens of now-defunct galaxies. This lumpiness is the key to understanding galactic evolution. A smooth halo would suggest a quiet, isolated history. The spectacular lumpiness we observe confirms the dominant theory of hierarchical structure formation, that galaxies build themselves up over time through a continuous process of merger and accretion. Andromeda's halo is the ultimate case study, a dynamic archive that records every major interaction it has ever experienced, providing a timeline of cosmic events that stretches back to the galaxy's very origins. As our exploration of the halo continues, we encounter a world that is both a close companion and a study in stark contrasts: the dwarf elliptical galaxy known as NGC 147. From a distance, it appears as a soft, ethereal glow, a ghostly patch of light against the blackness of space. It is not a mere cluster of stars, but a true galaxy in its own right, albeit a small and subdued one, orbiting Andromeda as its loyal satellite. Zooming in with powerful telescopes reveals its nature: a smooth, featureless ellipsoid of ancient stars, devoid of the vibrant spiral arms or glowing nebulae that characterize more active galaxies. Its very serenity tells a story of a long and quiet existence on the outskirts of a giant. But this tranquility is deceptive. The orbit of NGC 147 is a cosmic dance with its massive partner, a gravitational tango that has shaped its destiny for billions of years. Precise measurements of its movement show that it, along with its close neighbor the dwarf galaxy NGC 185, is on a vast, looping path around Andromeda. Orbital animations bring this relationship to life, tracing a wide, graceful arc that keeps it forever bound within the galaxy's immense gravitational influence. This isn't a static relationship, it's a dynamic interaction that has left its mark. As NGC 147 swings through the outer reaches of Andromeda's halo, it experiences tidal forces, the relentless gravitational tug from the larger galaxy. These forces act like a cosmic hand, subtly stretching and distorting the dwarf galaxy, pulling ever so gently at its outermost stars. This tidal interaction has had a profound impact on NGC 147's very structure and history. The most telling evidence is found in its population of globular clusters. For a galaxy of its modest size and mass, it possesses a surprising number of these dense, spherical star clusters. The prevailing theory among astronomers is that this abundance is a direct result of its galactic dance. The tidal forces exerted by Andromeda may have actually stimulated the formation of these clusters billions of years ago by compressing giant clouds of gas within the dwarf galaxy, triggering intense bursts of star birth that led to these tightly bound stellar cities. Furthermore, deep imaging has revealed the presence of extremely faint, distant stars that are being gradually stripped away from NGC 147, forming a tenuous stream that trails behind it in its orbit, a visible scar from its continuous gravitational encounter. The star formation history of NGC 147, read like a book from the light of its stars, tells a story of a very early and very final burst of activity. The vast majority of its stars are ancient, aging red giants and faint, low-mass stars that are many billions of years old. Their spectra show they are metal-poor, meaning they formed from primordial gas that had not been heavily enriched by previous generations of supernova. This indicates that NGC 147 experienced a powerful initial starburst shortly after it formed, creating its entire stellar population in a relatively short cosmic time. Then something happened. The galaxy effectively died. Its star formation shut down completely and has not resumed since. The reason for this quenching is directly linked to its relationship with Andromeda. As it fell into the larger galaxy's halo, the process likely stripped away any remaining reservoirs of cold gas, the essential fuel for creating new stars. Without this raw material, the galaxy's stellar engine simply shut down, leaving it a fossilized relic of an earlier era. Despite its quiet nature, NGC 147 plays a pivotal role as a key satellite for astronomers. It serves as a critical control sample for understanding the complex physics of galaxy evolution. By studying its straightforward structure and simple stellar populations, scientists can test models of how dwarf galaxies form and how they are affected by their environment. Its well-mapped orbit allows for incredibly precise measurements of the total mass of the entire Andromeda system, including its dark matter halo. By observing how the gravity of Andromeda tugs on NGC 147 and dictates its path, astronomers can weigh the entire galaxy, providing one of the most important data points in our quest to understand the invisible material that dominates the cosmos. This faint, serene satellite, therefore, is far more than a passive ornament. It is an essential tool, a natural laboratory whose quiet history helps us decode the violent and dynamic processes that govern all galaxies. Yet our next object shows that even a close encounter can be destructive, revealing the process of galactic cannibalism in stunning, real-time detail. While NGC 147 maintains a serene distance, another of Andromeda's satellites, the dwarf elliptical galaxy known as NGC 205 or Messier 110, is paying a much heavier price for its proximity. This small galaxy, a familiar sight in deep sky images clinging close to Andromeda's bright core, is currently being torn apart. The evidence is a magnificent and immense tidal tail, a vast stream of stars that has been gravitationally plucked from its body, stretching across tens of thousands of light-years of dark space. This isn't a subtle feature. In long-exposure photographs taken with the world's most powerful telescopes, this stellar stream is clearly visible as a faint, ethereal ribbon of light, a cosmic brushstroke painted by the relentless force of gravity. The creation of this tail is a direct and violent consequence of NGC 205's orbit, bringing it too close to its gigantic neighbor. As the dwarf galaxy swings through the inner regions of Andromeda's halo, it experiences an extreme difference in gravitational pull across its structure, a phenomenon known as a tidal force. The side of the dwarf galaxy facing Andromeda is pulled much more strongly than the side facing away. This difference acts like a cosmic stretching machine, distorting the galaxy's shape and eventually pulling material away entirely. The process is slow by human standards but inevitable on a cosmic timescale. The stars that are stripped away don't just vanish, they are flung into new orbits, tracing the path that the dwarf galaxy has taken and forming this spectacularly long tail that now acts as a permanent record of the interaction. The stars within this stream tell their own ancient story. Spectroscopic analysis reveals they are primarily old, population II stars characterized by their low metal content. This composition indicates they were among the first stars to form in NGC 205 itself, ancient citizens that have now been exiled. Their journey from the relative safety of their home galaxy into the lonely void of the tidal tail represents a fundamental transformation. They are no longer part of a cohesive gravitational family but have become orphans, forever bound to the larger galaxy that claimed them. The very existence and length of this tail allow astronomers to perform a kind of celestial archaeology, working backwards to calculate the precise orbital dynamics that led to this stellar theft, including the mass of Andromeda and the number of close passes NGC 205 has endured. This ongoing demolition derby between Andromeda and NGC 205 is one of the clearest and most visually dramatic examples of hierarchical structure formation in action. It shows us that galactic cannibalism isn't just a theoretical event from the distant past. It is a process that continues to this day in our own local cosmic neighborhood. The tidal tail is a snapshot of a galaxy in the process of being consumed, a midway point between a sovereign dwarf galaxy and the completely assimilated stellar streams we find elsewhere in the halo. By studying its detailed structure and the motion of its stars, astronomers gain a profound understanding of the mechanics of galaxy mergers, witnessing the forces that have built great galaxies like Andromeda over billions of years, one devoured companion at a time. Drifting in the immense loneliness of the halo, far from the crowded stellar cities of the disk, we find a pair of stars locked in a gravitational embrace so peculiar it challenges our understanding of how such duos form. This is not a typical binary system where two similar stars are born together from the same natal cloud and orbit each other in a stately, predictable dance. Instead, this system is a cosmic odd couple, a mismatched pair whose very existence suggests a past filled with violent gravitational upheaval. When astronomers first measured the properties of this binary, the data revealed a stunning asymmetry. One star is a relatively lightweight, sun-like star, while its companion is a massive, brilliant behemoth many times heavier. Their orbital dance is just as strange, tracing a wildly elliptical path rather than a neat circular one, as if their connection is both powerful and profoundly unstable. To visualize this, binary orbit diagrams are essential. A typical binary system might display two stars of similar size, with orbits represented by two neat concentric circles or a very slight ellipse, indicating a stable, long-term relationship forged in a calm nursery. The diagram for this system looks completely different. It shows a massive central dot representing the primary heavy star, with a much smaller dot for its lightweight companion tracing a long, skinny, oval path around it. The eccentricity of this orbit is extremely high, meaning the two stars spend most of their time far apart, only to swing in dangerously close at periastron, their point of closest approach, before being flung back out into the vast reaches of their shared space. This is not the placid waltz of a born-together pair. This is a chaotic, passionate tango that hints at a dramatic origin story. So how does such an unusual partnership come to be in the relative isolation of the halo? The calm, in situ formation theory, where two stars condense from a single rotating gas cloud, struggles to explain the drastic mass difference and the extreme orbit. A turbulent cloud might produce some variation, but not to this degree. Astronomers therefore turn to a far more dynamic and thrilling explanation, a gravitational encounter. The halo, for all its sparse population, is a dynamic environment where stars and clusters slowly orbit the galactic center, occasionally crossing paths over billions of years. The leading theory posits that both of these stars were once single, minding their own business in different parts of the halo or perhaps within a loose cluster. A motion simulation brings this theory to life. We see the future heavy star drifting through space. Meanwhile, the lighter star is part of a different, widely separated binary system. Through a chance gravitational encounter, the heavy star passes a little too close to this pre-existing binary. The complex three-body interaction that follows is a gravitational game of musical chairs. Energy is transferred, and the lightweight star is effectively stolen from its original partner and captured by the interloping heavy star. The energy of this chaotic exchange is imprinted on the new pair, leaving them in this wide, eccentric orbit that we see today. It's a celestial spouse swap orchestrated by the invisible hand of gravity millions of years ago. This formation mechanism makes such binary systems incredibly valuable to astronomers. They are not just curiosities, they are living records of past dynamical interactions in the galaxy. Their orbital parameters act as a fossilized signature, allowing scientists to run sophisticated computer models backwards in time to recreate the precise conditions of the encounter that created them, giving us a unique window into the gravitational history of the halo itself. Now, our exploration takes us to perhaps the most fundamental and elusive component of the galactic halo, the very stuff that holds it all together. Deep within Andromeda's vast sphere of influence, astronomers have found compelling, albeit indirect, evidence for a massive and completely invisible structure, a dark matter subhalo. To understand what this means, picture the main halo of Andromeda not as a smooth, featureless cloud of dark matter, but as a gigantic swarm of even smaller, denser clumps, each one a self-contained knot of this mysterious substance. These are the subhalos, the cosmic building blocks of the larger dark matter web. Finding one is incredibly difficult because by definition they emit no light. Their presence can only be inferred by the gravitational influence they exert on the one thing we can see, the stars moving around them. The search for this particular subhalo involved a meticulous stellar census. Astronomers used the light-gathering power of telescopes like the Keck Observatory in Hawaii to perform a technique called stellar kinematics. They didn't just count the stars in a specific patch of the halo, they precisely measured their motions. By observing the subtle shifts in the wavelength of starlight, the Doppler effect, they could calculate how fast each star was moving towards or away from us, plotting their radial velocities. In one region, the data revealed something peculiar. The stars weren't all moving at a similar, sedate pace as you might expect in a quiet part of the halo. Instead, their velocities were wildly varied, with some stars zipping along at high speed while others drifted slowly. This chaotic spread in velocity is formally known as velocity dispersion. A graph of this data is the key piece of evidence. Imagine a simple chart on screen. On the horizontal axis, we have the measured velocity of each star. On the vertical axis, we have the number of stars moving at that speed. In a region dominated only by the smooth, overall pull of Andromeda's main halo, this graph would show a tight, narrow peak. Most stars would share a similar velocity with a little natural variation. The graph for this region looks completely different. It shows a very broad, flattened distribution. The peak is wide and low, meaning the velocities of these stars are all over the place. This high-velocity dispersion is the telltale signature of a deep, localized gravitational well. Something massive and unseen must be lurking there, its gravity tugging fiercely on the surrounding stars, accelerating some and slowing others, creating this statistical frenzy of motion. From the width of that velocity dispersion graph, astronomers can actually calculate the mass of the invisible object causing the disruption. The math is complex, but the principle is based on the same physics that allows us to weigh the Sun by measuring Earth's orbital speed. The greater the spread in the star's velocities, the more mass is required to generate the gravitational field that's whipping them around. The estimates for this subhalo are staggering. It appears to contain a mass equivalent to hundreds of millions, perhaps even a billion suns. And yet, when we look at that exact spot with every wavelength of light we have, we see nothing but a few faint, ancient stars. The overwhelming majority of that mass is completely dark, a ghostly concentration of matter that reveals itself only through its relentless gravitational pull. The existence of such a structure is a critical test for our leading cosmological model, known as lambda cold dark matter, or lambda CDM. This model describes a universe whose structure is shaped by slow-moving or cold dark matter particles. A key prediction of this model is that large dark matter halos, like the one enveloping Andromeda, should be teeming with thousands of smaller subhalos. They are the leftover remnants from the hierarchical assembly of the galaxy. Finding them and confirming their properties is essential for validating our entire understanding of how the cosmos evolved from a smooth soup after the Big Bang into the intricate web of galaxies we see today. If we couldn't find these subhalos, it would mean our model is wrong, and we'd have to go back to the drawing board. This particular subhalo candidate in Andromeda's halo is more than just a number in a data set. It's a profound confirmation of a theoretical prediction. Its mass and size fit neatly within the expectations of the lambda CDM model, acting as a crucial data point that helps shore up our most fundamental theories of the universe. It shows that dark matter does indeed clump and cluster on these smaller scales, just as the models have always said it should. Every such subhalo we can identify brings us one step closer to understanding the true nature of this invisible cosmic scaffolding, proving that even in the emptiness of intergalactic space, the hidden architecture of the universe is constantly at work, shaping everything we see. While the halo is filled with objects that orbit Andromeda, our next discovery is a celestial body that seems to have one foot out the door, a star cluster that appears to be in the process of leaving the galaxy entirely. This is an intergalactic star cluster, a tightly bound family of hundreds of thousands of stars that is situated so far out in the halo it almost seems untethered. In deep-field astronomical images, it appears as a single, faint smudge of light, a lonely island of stars adrift in a sea of blackness, with the magnificent spiral of Andromeda itself looming in the distance as a stark reminder of the community it has left behind. Precise measurements of its distance confirm its incredible isolation. It is so far from the galactic center that it exists in a gravitational no-man's land on the very edge of Andromeda's influence. The central mystery of this cluster is its origin story, and astronomers are grappling with two equally compelling but opposite theories. The first is a tale of violent ejection. In this scenario, the cluster was once a resident of Andromeda's bustling disk or inner halo. Through a dramatic gravitational interaction, it was flung out into the void. The most likely culprit for this cosmic catapult is Andromeda's central supermassive black hole. If a binary star system or another dense object ventured too close to the black hole, the complex three-body gravitational dance that followed could have transferred immense energy to our cluster, hurling it away on a trajectory so extreme it may never return. Alternatively, it could have been ejected during a close encounter with another massive object, like a giant molecular cloud, or during the chaotic collision of two galaxies, where it was simply a bystander caught in the gravitational crossfire. The second theory is far more primordial and just as fascinating. It suggests this cluster was never truly a part of Andromeda to begin with. Instead, it might be a true intergalactic wanderer, a free-floating entity that formed in the vast, empty filaments of the cosmic web. In the early universe, there were immense reservoirs of gas that existed in the spaces between the first proto-galaxies. It is conceivable that in one of these lonely pockets, a cloud of gas became dense enough to collapse and form a star cluster entirely on its own, a celestial sovereign state that has been drifting through the intergalactic void for billions of years, only now being slowly captured by the outskirts of Andromeda's immense gravitational field. Its chemical composition holds the key to distinguishing between these stories. If its stars are metal-rich, showing elements forged in previous stellar generations, it likely formed within a galaxy and was ejected. If it is metal-poor, pristine, and ancient, it could very well be a primordial artifact, a rare survivor from a time before galaxies dominated the cosmos. Studying such an isolated object presents immense challenges for astronomers. Its extreme distance makes it incredibly faint, demanding long exposure times on the world's largest telescopes just to resolve its individual stars. Determining its precise motion is even more difficult. We need to track its subtle movement across the sky over years or even decades to understand if it is truly bound to Andromeda or just passing through. This requires comparing images taken far apart in time with painstaking precision to measure its proper motion, a tiny shift against the background of infinitely distant galaxies. Furthermore, without any surrounding gas or other clusters for context, it exists in a vacuum, making it difficult to piece together its history from its environment alone. It is a celestial puzzle with most of the pieces missing, forcing us to rely on sophisticated computer simulations to model every possible scenario of its birth and exile. This lonely cluster is more than a curiosity. It is a stress test for our models of dynamics and galaxy formation, a single point of light that challenges our understanding of where celestial objects can form and how they can travel. Tucked away in the sparse vastness of the halo, a delicate cosmic flower blooms, a fleeting spectacle of stellar death that holds profound secrets about life in the galactic frontier. This is a planetary nebula, a glowing shell of gas ejected from a dying star. While such nebulae are found throughout galaxies, discovering one this far out in the lonely halo of Andromeda transforms it from a common sight into a rare and precious laboratory. In false color images, often composed from observations in the specific light of oxygen, hydrogen, and nitrogen, it appears as a stunningly intricate structure. We might see a brilliant turquoise ring, the signature of doubly ionized oxygen, surrounded by a more diffuse crimson glow of hydrogen alpha emission, perhaps with delicate filamentary structures or bipolar jets suggesting a complex and violent ejection history. This beautiful, ghostly apparition is the final testament of a star that lived and died in near total isolation. The very existence of a planetary nebula here is our first clue. It tells us that a star of low to intermediate mass, similar to our Sun, reached the end of its life in this remote location. For billions of years, this star would have burned steadily, a solitary beacon in the dark. As it exhausted its nuclear fuel, it swelled into a red giant, its outer layers becoming tenuous and weakly bound. In its final throes, it began to pulsate, eventually expelling these layers into the surrounding void in a series of energetic outbursts. The exposed, intensely hot core of the star, now a white dwarf, flooded this expanding shell of its own remains with ultraviolet radiation, causing the gas to fluoresce with that characteristic and beautiful glow. This entire life cycle, from birth to this magnificent death, played out far from the dense, gas-rich environments of the galactic disk where such events are common. Its composition, read like a chemical biography through its spectrum, is what makes it truly invaluable. When astronomers direct a spectrograph at this faint glow, they don't just see the bright emission lines that create the beautiful images. They see a detailed inventory of the elements present within the nebula gas. The strength of these spectral lines reveals the elemental abundances, the precise amounts of hydrogen, helium, oxygen, nitrogen, carbon, and other trace elements that were forged in the star's core and dredged up to its surface during its death phases. For a star that formed in the halo, this chemical fingerprint is expected to be pristine, metal-poor, and simple, reflecting the primordial gas from which it condensed billions of years ago. However, the spectra from this particular nebula might tell a more complicated and fascinating story. The ratios of certain elements, like nitrogen to oxygen or helium to hydrogen, can appear enhanced or unusual compared to planetary nebulae found in the galactic disk. This anomalous chemistry is a direct consequence of its low-density environment. In the crowded disk, a star can sometimes accrete extra material from interstellar space or be influenced by the magnetic fields or winds of neighboring stars, subtly altering its evolution. But out here in the quiet halo, this star evolved in perfect isolation. Any changes in its composition were driven purely by its own internal nuclear processes without any external contamination. This makes its spectrum a pure, uncontaminated record of how a single star of a specific mass processes its elements when left entirely to its own devices. It provides a critical baseline for stellar astrophysics, allowing us to test our models of nucleosynthesis and dredge up events against a perfectly controlled natural experiment. Studying the death of this one star, therefore, gives us a clearer window into the life and death of all stars. The intricate structures visible in the false color images, the rings, the jets, the asymmetrical lobes, also hold clues. Their shape is dictated by the complex physics of the mass loss process. Was the star a single pulsating giant, or did it have a binary companion whose gravity helped sculpt the outflow into such a distinct form? In the halo, where stellar encounters are vanishingly rare, a bipolar structure is more likely the result of a binary system than any external influence, providing evidence that even out here, stars can have companions. This lonely, glowing shroud is far more than a pretty picture. It is a detailed autopsy report of a star that lived a long and quiet life on the edge, its final, brilliant act illuminating the fundamental principles that govern stellar evolution across the entire universe. But for all the ancient, slow-moving relics we've found, the halo also holds objects of incredible, violent energy. Our next discovery is a beacon of powerful radiation, a high-energy X-ray source that burns brightly against the cosmic darkness. This isn't a gentle glow of starlight. It's a searing, rhythmic blast of high-frequency photons, detected by space-based observatories like NASA Chandra X-ray Observatory and the European Space Agency's Newton. When astronomers overlay these precise X-ray detections onto optical images of the halo, a single, brilliant pinpoint of light appears, a stark contrast to the faint, ancient stars that surround it. This isn't just a little extra energy. This source is pouring out X-rays with a luminosity that can rival entire star clusters, signaling a cosmic powerhouse operating in a place where we expected only quiet and decay. The immediate question is, what could possibly generate such intense energy in this stellar backwater? Astronomers have two prime suspects, both remnants of massive stellar death. The first is a stellar mass black hole. This wouldn't be the supermassive monster at a galaxy's center, but a smaller, yet still fiercely energetic version. It could be the corpse of a star 20 times more massive than our Sun that collapsed in on itself. If this black hole is locked in a tight orbit with a companion star, its immense gravity can rip material from the surface of that star. This stolen gas doesn't fall in directly. It spirals down into an incredibly hot, whirling disk around the black hole, an accretion disk where friction heats the material to millions of degrees, causing it to blaze with X-rays before it finally crosses the event horizon and vanishes forever. The second compelling candidate is a neutron star, the other possible outcome of a supernova explosion. A neutron star is a city-sized ball of unimaginably dense matter, where a sun's worth of mass is crushed into a sphere just a few miles across. A teaspoon of its material would weigh billions of tons. If this neutron star is also in a binary system and is spinning rapidly, what we call a pulsar, it can generate powerful magnetic fields and beams of radiation that sweep across space like a cosmic lighthouse. If one of those beams points toward Earth, we detect it as a pulsating source of X-rays. Alternatively, it could be accreting matter from a partner in a similar way to a black hole, heating the incoming gas to X-ray temperatures on its incredibly hard surface. The profound puzzle isn't just the source itself, but its location. Objects like this are the products of massive, short-lived stars. Such stars are not born in isolation. They form in the dense, gas-rich nurseries of a galaxy's spiral arms or central bulge. Their lives are measured in mere millions of years, a cosmic blink of an eye. For one of their remnants to be found this deep in the halo means it must have experienced a truly dramatic journey. It could not have formed where we see it today. This leads to a fascinating cosmic detective story. This black hole or neutron star must have been born in the crowded disk of Andromeda and then violently kicked out. The mechanism for such a stellar ejection is as dramatic as it is elegant. When a massive star dies in a supernova, the explosion is not always perfectly symmetrical. If there is a slight imbalance, the resulting shockwave can act like a rocket engine, imparting a massive kick to the newborn remnant. This natal kick can be powerful enough to fling a neutron star or even a black hole clear out of the galactic disk and into the halo at tremendous speeds, turning it into a high-velocity rogue. There's another, even more thrilling possibility. This X-ray source could be the signature of an intermediate mass black hole, a long-sought missing link between the common stellar mass black holes and the supermassive giants that rule galactic centers. While its energy output is high, it could be consistent with a black hole hundreds or thousands of times the mass of our Sun. The idea that such an object could be wandering alone through the halo is a startling one. It might be the stripped core of a dwarf galaxy that Andromeda consumed long ago, its stars scattered to form a stream like the Giant Stream, while its dark heart, the black hole that once anchored it, was left to drift silently in the darkness, now revealing itself only by the faint glow of a captured star it is slowly consuming. Each pulse of X-ray light is a clue, a data point in an ongoing investigation into the most energetic and secretive objects in the universe, proving that even in the deepest darkness, the aftermath of stellar catastrophe can shine with unmistakable intensity. Yet as we map the grand, chaotic tapestry of Andromeda's halo, some of its most intriguing features are not the obvious streams or massive objects, but subtle, mysterious concentrations of light that challenge our senses of the galaxy's population. One such feature is a stellar overdensity, a region where the number of stars per cubic light year is unexpectedly and inexplicably high. To the unaided eye, even through a powerful telescope, this area might not look special at all, just another patch of the faint, smooth glow that defines the halo. Its discovery was not a matter of spotting a new smudge in an image, but a triumph of statistical astronomy and painstaking data analysis. It emerged from massive surveys like the Pan-Andromeda Archaeological Survey, where astronomers didn't just look at the sky, they counted. They meticulously catalogued the positions and brightness of millions upon millions of individual stars across the entire halo, building a gigantic three-dimensional map of its stellar population. The reveal comes when this vast data set is processed to create a density map. Imagine a standard optical image of this part of the halo, a mostly black field sprinkled with tiny, faint points of light. Now a visual overlay appears on screen, a soft, translucent heat map of color. Most of the area is a cool, deep blue, indicating the expected, sparse distribution of stars. But right in the center of the frame, a distinct, warm blob of orange and red blossoms, a clear sign that in this specific pocket of space, stars are significantly more crowded together than in the surrounding void. This isn't a tightly bound globular cluster with a sharp edge. It's a diffuse but undeniable clustering, a stellar crowd gathered in the cosmic wilderness for reasons we don't yet fully understand. So what causes such a gathering of stars in a region where matter is usually so scarce? Astronomers are investigating several compelling origins, each telling a different story about the halo's violent history. The first and most straightforward explanation is that this is the faint, dissolving remnant of a globular cluster that has spent billions of years being pulled apart by Andromeda's gravity. Globular clusters are incredibly dense when they form, but as they orbit the galaxy, they continuously pass through the disk and the inner halo. With each pass, tidal forces the difference in gravitational pull from one side of the cluster to the other act like a gravitational hand, plucking stars from the cluster's outer layers and scattering them along its orbital path. This overdensity could represent the cluster's fading core, the last dense grouping of stars that still remember their shared origin, while their lost siblings now form a faint, leading or trailing tidal tail that is too diffuse for our current telescopes to easily detect. Another, more dramatic possibility is that this is all that remains of a dwarf galaxy that was cannibalized by Andromeda long ago. In the hierarchical model of galaxy formation, large galaxies grow by consuming smaller ones. When a dwarf galaxy is pulled in, it doesn't just vanish, it is stretched and shredded into streams. Sometimes the densest core of that dwarf galaxy, the very heart where its stars were most tightly packed, can resist complete dissolution for a very long time. This overdensity could be that surviving core, a ghostly galactic nucleus that has been orbiting Andromeda for billions of years since its parent galaxy was destroyed. Its stars would share a common velocity and a distinct, ancient chemical signature, a metal-poor composition that marks them as survivors from the universe's early chapters. Distinguishing between these two scenarios, a dying cluster or a galactic core, requires more than just a density map. Astronomers turn to the subtle details hidden in the starlight itself. They use spectrographs to measure the radial velocities of dozens of individual stars within the overdensity. If they all share a very similar motion, it strongly suggests they are a coherent, gravitationally bound structure, like the remnant core of a dwarf galaxy. If their motions are more random, it points to a structure that is already well on its way to dissolving into the general halo population. Furthermore, deep photometry that measures the color and brightness of the stars can create a color magnitude diagram. The specific pattern of where the stars fall on this diagram, the unmistakable turn-off point of the main sequence and the location of the red giant branch reveals the population's age. A single ancient age for all the stars would be the signature of a globular cluster remnant, while a slightly broader range of ages might hint at the more complex star formation history of a devoured dwarf galaxy. This single faint patch of light, then, is far more than a statistical anomaly. It is a crime scene under investigation, a puzzle box holding clues to a past event of cosmic demolition. Whether it is the final breath of a star cluster or the enduring heart of a vanquished galaxy, its continued existence helps us piece together the rate and scale of galactic accretion events that have built Andromeda over time. By studying its properties, we can better understand the survival times of dense structures within the hostile tidal environment of a galactic halo, refining our models of how galaxies evolve through consumption and how their histories are written in the faint, clustered light of their most ancient stars. Amid the sparse and ancient stellar population of the halo, a single, faint point of light reveals a fascinating and beautiful anomaly, a star that has, in its old age, transformed itself into a cosmic jewel. This is a carbon star, a rare type of giant star whose atmosphere has become so enriched with carbon that it fundamentally changes its chemistry and its appearance. While other stars in the halo burn with a pale, white or reddish light, this one, when viewed through a telescope equipped with specific filters, glows with a deep, distinctive crimson hue. Its very color is a flag it waves, signaling its unique and advanced stage of life to anyone who knows how to look. This star's journey to becoming a carbon star is a story written in nuclear fusion and stellar winds. It began its life billions of years ago as a modest star, not too different from our Sun but with a slightly higher initial mass. For eons, it fused hydrogen into helium in its core, living a quiet existence. As it aged and exhausted its hydrogen fuel, it swelled into a red giant, its outer layers expanding and cooling. Deep within its heart, the intense heat and pressure began a new chapter of fusion, converting helium into carbon. In most stars, this newly forged carbon remains trapped deep within. But in this star, a process called dredge-up occurred, where powerful convection currents act like a celestial elevator, carrying the carbon from the burning depths up to the star's visible surface. This is where the magic happens. In the star's cooler outer layers, carbon atoms readily link together, forming molecules like carbon monoxide and, crucially, silicon carbide. These molecules have a powerful effect on the star's light. A graphic spectral analysis makes this transformation stunningly clear. Imagine a standard stellar spectrum for a typical red giant, a rainbow band of color crossed by dark absorption lines with particularly strong lines for elements like titanium oxide. Now the spectrum for this carbon star appears beside it. It looks completely different. The titanium oxide lines are gone, replaced by the overwhelming presence of carbon compounds. Broad, dark swaths caused by molecules of C2, known as the swan bands, dominate the spectrum, effectively blotting out the blue and violet light. This is why the star appears so red to our eyes. Its atmosphere is literally filled with a sooty haze of carbon dust, filtering its own light and giving it that rich, ruby glow. The presence of such a star in the remote halo is a vital clue for astronomers. Its very specific and complex chemistry tells us two important things. First, it indicates an advanced age. It takes a very long time for a star of this mass to go through its entire life cycle, exhaust its core hydrogen, swell into a giant, and then undergo third dredge up to become a carbon star. This isn't a star from a recent generation. It is an ancient resident that has been evolving in place for billions of years. Second, its isolated location confirms it was born in the halo itself, from the pristine, metal-poor gas that existed there long ago. It is not an immigrant from the disk, it is a native of the galactic frontier. This makes it a perfect standard candle for mapping the halo's structure. Carbon stars are incredibly luminous, and their distinctive spectral signature makes them easy to identify even at vast distances. Astronomers can conduct wide-field surveys, scanning the skies around Andromeda and simply tagging every carbon star they find. Because these stars all have roughly the same intrinsic brightness, their apparent faintness directly tells us their distance. By plotting the three-dimensional positions of hundreds of these crimson beacons, scientists can create a precise point cloud map of the halo's extent, revealing its true shape, its density variations, and even the ghostly imprints of past mergers in the form of clustered groups of these stars. This one aging giant, burning with a sooty red light, becomes a brilliant lantern in the darkness, helping to illuminate the architecture of the entire galactic halo and trace the history of its earliest stars. Yet the story of Andromeda's violent growth is written not only in the grand, sweeping arcs of entire dwarf galaxies, but also in the fine, delicate brushstrokes left by its smaller, more peculiar companions. Among its collection of satellites, one stands out for its bizarre nature: the compact elliptical galaxy known as Messier 32, or M32. This tiny, incredibly dense galaxy is a cosmic paradox, a powerhouse of stellar concentration orbiting its giant neighbor. And recent observations have revealed that this intense little galaxy has not been a passive companion. It has been stirring the pot, leaving behind a faint but distinct trail of stellar debris that winds through the halo, a ghostly signature of past gravitational encounters. The discovery of this tidal debris was a feat of observational patience. It required sifting through the deep, wide-field survey data from projects like P&S, looking for the most subtle of patterns. What astronomers found was not a massive, coherent stream like the Giant Stream, but something more delicate and fragmented, a faint sprinkling of stars with a shared motion and chemistry that traces a path leading directly back to M32. Visualizing this with an illustrated tidal stream overlay is crucial. Imagine a standard image of the region around Andromeda with its smooth background halo. Then a new graphic layer fades in, a faint glowing ribbon of blue and white, a bit like a wisp of celestial smoke curling through the darkness. This is the tidal stream, a visual representation of the overdensity of stars that have been gravitationally stripped from their parent galaxy. The stream appears thin and tenuous, a clear indication that M32, for all its density, is a relatively small galaxy that has lost only a fraction of its stars to the pull of its giant neighbor. The very existence of this stream tells a dramatic story of a close encounter. For M32 to be losing stars, it must have ventured perilously close to Andromeda's disk in the relatively recent cosmic past. Computer simulations of this interaction are both violent and beautiful. They show the compact galaxy, a tight sphere of stars, making a close pass by the immense disk of Andromeda. As it does, the difference in gravitational pull between the side of M32 facing Andromeda and the side facing away, the tidal force becomes overwhelming. This force acts like a gravitational hand, reaching into the satellite galaxy and plucking the stars from its outer layers. Because M32 is so dense, its core remains largely intact, but its outskirts are stretched and pulled, the stolen stars flung into new orbits that now form this long, trailing stream of cosmic debris. This process is a slower, more gentle version of the destruction that created the Giant Stream, a testament to the fact that galactic interactions occur on a spectrum, from complete annihilation to a gradual nibbling away. The stars within this stream are messengers from M32 itself, and their chemical composition holds fascinating clues. Spectroscopic analysis reveals they are surprisingly metal-rich, meaning they contain a higher abundance of elements heavier than hydrogen and helium compared to the typical ancient metal-poor stars of the halo. This is a direct fingerprint of their origin. M32 is not a primordial dwarf galaxy. It is thought to be the stripped core of a much larger galaxy that was previously cannibalized by Andromeda. The stars now in the tidal stream were forged in that larger, more evolved galaxy, which had ample time to create and recycle heavy elements through generations of stars. Their presence in the halo adds a new layer of chemical complexity, mixing this enriched material with the pristine, ancient stars that dominate the region. This stream is therefore more than just a gravitational artifact. It is a pipeline delivering chemically processed building blocks from a dense, evolved system into the vast, more primitive reservoir of the halo. This ongoing interaction provides a unique window into the resilience of a dense galactic core. M32 is famously compact, with a phenomenal concentration of stars packed into a very small volume. This high density is its armor, helping it to resist the tidal forces that have completely dismantled less robust galaxies. The tidal stream shows us that while Andromeda is successfully stripping its outer layers, the heart of M32 remains defiantly intact. By studying the rate of mass loss and the density profile of the stream, astronomers can effectively perform a cosmic stress test, measuring the gravitational binding energy of M32 and gaining insights into the conditions that allow a galactic nucleus to survive a close encounter with a giant. This tiny, dynamic satellite and the faint trail it leaves behind are a living demonstration of the continuous and complex processes of accretion and disruption that relentlessly shape and add intricate detail to the ever-evolving galactic halo. But for all the ancient, slow-moving relics we've found, the halo also holds objects of incredible, violent energy. Our next discovery is a beacon of powerful radiation, a high-energy X-ray source that burns brightly against the cosmic darkness. This isn't a gentle glow of starlight. It's a searing, rhythmic blast of high-frequency photons detected by space-based observatories like NASA Chandra X-ray Observatory and the European Space Agency's Newton. When astronomers overlay these precise X-ray detections onto optical images of the halo, a single, brilliant pinpoint of light appears, a stark contrast to the faint, ancient stars that surround it. This isn't just a little extra energy. This source is pouring out X-rays with a luminosity that can rival entire star clusters, signaling a cosmic powerhouse operating in a place where we expected only quiet and decay. The immediate question is, what could possibly generate such intense energy in this stellar backwater? Astronomers have two prime suspects, both remnants of massive stellar death. The first is a stellar mass black hole. This wouldn't be the supermassive monster at a galaxy's center, but a smaller, yet still fiercely energetic version. It could be the corpse of a star 20 times more massive than our Sun that collapsed in on itself. If this black hole is locked in a tight orbit with a companion star, its immense gravity can rip material from the surface of that star. This stolen gas doesn't fall in directly. It spirals down into an incredibly hot, whirling disk around the black hole, an accretion disk where friction heats the material to millions of degrees, causing it to blaze with X-rays before it finally crosses the event horizon and vanishes forever. The second compelling candidate is a neutron star, the other possible outcome of a supernova explosion. A neutron star is a city-sized ball of unimaginably dense matter, where a sun's worth of mass is crushed into a sphere just a few miles across. A teaspoon of its material would weigh billions of tons. If this neutron star is also in a binary system and is spinning rapidly, what we call a pulsar, it can generate powerful magnetic fields and beams of radiation that sweep across space like a cosmic lighthouse. If one of those beams points toward Earth, we detect it as a pulsating source of X-rays. Alternatively, it could be accreting matter from a partner in a similar way to a black hole, heating the incoming gas to X-ray temperatures on its incredibly hard surface. The profound puzzle isn't just the source itself, but its location. Objects like this are the products of massive, short-lived stars. Such stars are not born in isolation. They form in the dense, gas-rich nurseries of a galaxy's spiral arms or central bulge. Their lives are measured in mere millions of years, a cosmic blink of an eye. For one of their remnants to be found this deep in the halo means it must have experienced a truly dramatic journey. It could not have formed where we see it today. This leads to a fascinating cosmic detective story. This black hole or neutron star must have been born in the crowded disk of Andromeda and then violently kicked out. The mechanism for such a stellar ejection is as dramatic as it is elegant. When a massive star dies in a supernova, the explosion is not always perfectly symmetrical. If there is a slight imbalance, the resulting shockwave can act like a rocket engine, imparting a massive kick to the newborn remnant. This natal kick can be powerful enough to fling a neutron star or even a black hole clear out of the galactic disk and into the halo at tremendous speeds, turning it into a high-velocity rogue. There's another, even more thrilling possibility. This X-ray source could be the signature of an intermediate mass black hole, a long-sought missing link between the common stellar mass black holes and the supermassive giants that rule galactic centers. While its energy output is high, it could be consistent with a black hole hundreds or thousands of times the mass of our Sun. The idea that such an object could be wandering alone through the halo is a startling one. It might be the stripped core of a dwarf galaxy that Andromeda consumed long ago, its stars scattered to form a stream like the Giant Stream, while its dark heart, the black hole that once anchored it, was left to drift silently in the darkness, now revealing itself only by the faint glow of a captured star it is slowly consuming. Each pulse of X-ray light is a clue, a data point in an ongoing investigation into the most energetic and secretive objects in the universe, proving that even in the deepest darkness, the aftermath of stellar catastrophe can shine with unmistakable intensity. Nestled within the ancient stellar population of the halo, a star shines with a brilliant, youthful blue light that directly contradicts its surroundings. This is a blue straggler. It stands out like a vibrant sapphire against a field of faded rubies, a star that by all accounts should have died billions of years ago, but instead burns with the hot, energetic intensity of a much younger object. The very existence of such a star in this environment is a delightful paradox, a cosmic mystery that forces us to reconsider the quiet, predictable life cycles we assign to stars. To understand why this is so strange, we need to look at the life expectancies of stars. In a cluster or a population that all formed at the same time, the most massive stars are the rock stars of the universe. They live fast, burn bright with a blue-white intensity, and die young in spectacular supernova. The less massive stars are the slow burners. They are cooler, redder, and can persist for trillions of years. In the halo of Andromeda, where the stellar population is almost universally ancient, we expect to see only these long-lived, low-mass red stars. All the massive blue stars should have vanished eons ago. The blue straggler breaks this rule completely. When astronomers place it on a Hertzsprung-Russell diagram, the fundamental chart that plots a star's luminosity against its temperature, it doesn't fall in with the other old, cool red giants. Instead, it sits squarely in the region occupied by massive, young, main-sequence stars, shining with a temperature and brightness that proclaim it is very much in its prime. The central question is simple yet profound. How did this star cheat death? How did it find a fountain of youth in the galactic hinterlands? Astrophysicists have developed two compelling theories to explain this stellar rejuvenation, both involving dramatic interactions. The first is a direct stellar collision. While space is mostly empty, the core of a dense globular cluster is one of the few places where stars can occasionally come close enough to literally crash into one another. Picture two older, sun-like stars on a catastrophic collision course. Their gravitational pull draws them together faster and faster until they merge in a spectacular, fiery confluence. The result isn't destruction but creation. The merger product is a new, more massive star, its core reignited and its outer layers churned and mixed. This new star, born from the wreckage of its ancestors, has a new lease on life. With its increased mass, it burns hotter and brighter, appearing as a blue straggler that looks billions of years younger than its true chronological age. The second theory is a slower, more gentle process, but no less fascinating. It involves a vampire star in a binary system. Many stars in the halo are born in pairs, orbiting a common center of gravity. In one such system, you might have a larger star evolving faster than its smaller companion. As it ages, it swells into a red giant, its outer layers becoming tenuous and loosely bound. Its smaller, denser companion star then begins to act as a gravitational vampire, siphoning material from the giant's extended atmosphere onto itself. Over millions of years, the donor star is stripped down while the vampire star gorges on stolen gas. By accreting this extra mass, the vampire star is effectively reset. It becomes more massive, its nuclear furnace burns hotter, and it transforms into a brilliant blue straggler, while its companion is left as a stripped-down, helium-rich core. In both scenarios, the blue straggler isn't actually young. It's an old star that has been massively reinvigorated through a dramatic interaction, a cosmic makeover of the most extreme kind. The significance of these stars extends far beyond their curious appearance. They are natural laboratories for studying stellar evolution under extreme conditions. By analyzing their light with powerful spectrographs, astronomers can detect the chemical fingerprints of their formation. A blue straggler formed by collision should show signs of severe mixing, with elements normally buried deep in a star's core brought to the surface. One formed by mass transfer might show unusual chemical abundances or evidence of a faint, white dwarf companion, the corpse of the star it fed upon. Furthermore, because they are so bright, blue stragglers act as brilliant beacons, making them excellent tools for tracing the structure and extent of the very faintest parts of the halo. They light up the darkness, allowing us to map the distribution of matter and the gravitational forces at work in these remote regions. This paradoxical star, a youthful impostor in a field of ancients, provides a stunningly clear window into the dynamic and occasionally violent social lives of stars, revealing that even in the quietest corners of a galaxy, drama is always a possibility. But beyond the violent death of single stars and the faint glow of ancient suns, the halo holds an even more energetic and elusive secret, a whisper of radiation from the far end of the electromagnetic spectrum. Drifting through the vast expanse is a faint, diffuse fog of gamma rays, the most energetic form of light in the universe. This isn't a brilliant pinpoint like the X-ray source. It's a pervasive, incredibly faint glow that suffuses the entire halo, a background hum of high-energy photons detected not by optical telescopes, but by incredibly sensitive instruments on space-based observatories like the Fermi Gamma Ray Space Telescope. Mapping this emission is a monumental task. Astronomers must spend years collecting trillions of individual gamma-ray photons, then meticulously subtract all the known foreground and background sources, the brilliant pulsars, the distant active galaxies, the interactions of cosmic rays with gas in our own Milky Way. What remains is a subtle, residual excess, a faint but persistent signature that appears to originate from the extended halo of Andromeda itself. Gamma-ray sky maps are essential to visualizing this phenomenon. Imagine a full sky map with the central band of our own Milky Way stretching across the middle. Andromeda's position would be marked as a specific point. A standard map showing all detected gamma rays would be a chaotic splash of bright points and diffuse clouds. But when all the known point sources are digitally removed, a new image emerges. It shows a soft, extended glow centered on Andromeda, a roughly spherical cloud of gamma rays that extends far beyond the galaxy's visible disk, coiling around it like a faint, energetic aura. This is the diffuse emission, a halo of light that is invisible to our eyes but reveals a realm of profound particle physics playing out on a galactic scale. The central mystery and the source of great excitement among physicists is what exactly is producing these gamma rays. scientists are actively investigating two primary and radically different explanations. The first is a purely astrophysical source, cosmic rays interacting with interstellar gas. Cosmic rays are high-energy protons and atomic nuclei that constantly zip through space at nearly the speed of light. If these particles, accelerated by supernova shocks or other violent events within Andromeda, were to collide with the nuclei of atoms in the sparse gas of the halo, the impact could produce a shower of secondary particles, including neutral pions, which rapidly decay into pairs of gamma rays. This is a well-understood process observed in our own galaxy. The detected glow could simply be a sign that Andromeda's halo contains a vast reservoir of cosmic rays and a tenuous fog of gas that we haven't yet fully detected, their violent collisions illuminating the darkness with this faint, high-energy light. The second possibility is far more speculative and profoundly thrilling. It could be a signature of dark matter annihilation. This theory hinges on the idea that dark matter, which makes up the overwhelming majority of the halo's mass, might not be completely inert. Some leading theoretical models, particularly those involving weakly interacting massive particles or WIMP, suggest that when two dark matter particles collide, they could annihilate each other, converting their mass directly into energy according to Einstein's famous equation and producing a cascade of standard model particles, including gamma rays. The halo, with its immense density of dark matter, would be the perfect place to look for such a signal. The specific energy spectrum of the gamma rays, the precise distribution of their energies, could act as a fingerprint, potentially revealing the mass of the dark matter particle itself. If this interpretation were proven true, this faint, diffuse glow would be the first direct detection of the universe's most mysterious substance, a monumental breakthrough that would open a completely new window onto fundamental physics. Ongoing research efforts are focused on untangling these two possibilities. The key is in the details of the emissions distribution and its energy signature. Astrophysicists are creating incredibly sophisticated models of cosmic ray propagation, simulating how these particles would diffuse through the magnetic fields of the halo and interact with gas to produce gamma rays. They then compare these predictions to the actual Fermi data. If the gamma ray glow is concentrated in regions where traces of atomic hydrogen gas are also detected, it would strongly favor the cosmic ray interpretation. However, if the gamma ray distribution is smoother and more symmetric, matching the predicted distribution of dark matter in the halo rather than the clumpy distribution of gas, the dark matter hypothesis becomes much more compelling. Every new year of data from the Fermi telescope adds more photons to the count, sharpening the statistical significance of the signal and bringing us closer to understanding whether we are seeing the aftermath of mundane particle collisions or the first faint light from the invisible universe itself. Now, as we look deeper into the halo's stellar population, we encounter a group of objects that serve as cosmic clocks, their slow and predictable fading providing a direct timeline for the galaxy's most ancient events. This is a population of ancient white dwarfs, the Earth-sized cores of dead stars scattered throughout the halo. To the most powerful telescopes, they appear not as brilliant points of light, but as incredibly faint embers, cooling relentlessly into darkness over billions of years. Their discovery represents one of the greatest technical challenges in modern astronomy, requiring the exquisite vision of the Hubble Space Telescope to peer into the deepest reaches of the halo and distinguish these faint, ancient remnants from the countless background galaxies that speckle the image. Isolating them is a painstaking process of measuring subtle changes in their brightness over time and analyzing their distinct color, a pale blue or white hue that slowly reddens as they cool. The true value of these white dwarfs lies in their role as natural chronometers. A white dwarf has no internal fusion to keep it hot. It is simply a ball of degenerate matter, the exposed core of a star that has shed its outer layers. From the moment it forms, it begins a slow, inexorable cooling process. its temperature drops and its luminosity fades in a highly predictable way that astrophysicists understand intimately. This means that by simply measuring how dim a white dwarf has become its current luminosity, we can directly calculate its cooling age, the amount of time that has passed since the star ended its nuclear burning life and entered its final state. In the halo of Andromeda, these cooling ages are staggering, often exceeding 10 billion years, telling us that the stars that produced these white dwarfs died when the universe was in its youth. To unlock this timeline, astronomers rely on a powerful statistical tool known as the white dwarf luminosity function. Imagine a graph on screen. The vertical axis shows the number of white dwarfs counted, while the horizontal axis plots their brightness from brightest on the left to faintest on the right. In a population of stars that all formed at the same time, this graph would show a smooth curve that rises toward the fainter, cooler end and then abruptly plunges to zero. The point where that curve cuts off, where there are no white dwarfs fainter than a certain luminosity, is the critical data point. It marks the coolest and oldest white dwarfs that could have possibly formed in that population, defining the age of the entire group. By constructing this luminosity function for white dwarfs in different parts of Andromeda's halo, scientists can literally read the history of star formation and death across the galaxy's vast expanse. The story told by these fading embers is one of a dramatic and early beginning. The sheer number of ancient white dwarfs and the advanced cooling ages they reveal provide robust evidence that the halo's first stars formed in a tremendous initial burst of activity. This wasn't a slow, gradual build-up. It was a rapid and powerful ignition that lit up the proto-Andromeda Galaxy over a relatively short cosmic period. The parent stars of these white dwarfs were not the gentle sun-like stars we see today. They were more massive, living fast and dying young to leave behind these dense cores. Their pervasive presence confirms that the halo is the oldest component of the galaxy, a foundation laid down before the elegant spiral disk had even begun to form. Each faint point of light is a silent witness to the galaxy's violent and energetic birth, its steady cooling a timer that started ticking before our own solar system even existed. While the halo glows with the ancient light of dead stars and the invisible pull of dark matter, it also occasionally crackles with a different kind of energy, a sudden, unpredictable burst of radio waves that appears without warning and vanishes just as quickly. This brings us to the 23rd strange object in our list, a mysterious radio transient, a brief and brilliant shout in the silent wavelengths of the electromagnetic spectrum. Its discovery was not the result of a targeted search, but a moment of serendipitous pattern recognition within the vast, noisy data streams collected by radio observatories like the Very Large Array. Automated algorithms sifting through petabytes of observations flagged a single point of light that hadn't been there in previous scans of that precise patch of sky, a point that faded to nothing before anyone could even swing another telescope to take a second look. The signature of this event is captured in a radio light curve, a graph that tells a story of breathtaking speed and power. Imagine a simple chart on screen. The horizontal axis represents time, measured in hours or even minutes. The vertical axis shows the flux density or the sheer strength of the radio signal. For most of the timeline, the line is perfectly flat, hugging the bottom of the graph, representing the usual background radio silence of the halo. Then, without any preamble, the line rockets upward in a near-vertical spike, a dramatic crescendo of energy that peaks intensely before beginning a slower, more gradual decay back into silence. The entire event, from onset to disappearance, is incredibly brief, a celestial firework that flashes and is gone before you can truly process its presence. Astronomers are faced with a captivating puzzle. What natural engine could produce such a powerful, fleeting burst of radio energy in the relative emptiness of the galactic halo? The investigation immediately turns to known cosmic suspects. One compelling culprit is a type of flaring star, like a UV Ceti variable or a distant red dwarf. These stars are known to unleash colossal stellar flares, eruptions of magnetic energy that can accelerate electrons to near light speed, generating a burst of radio waves. However, the extreme luminosity of this transient and its location far from the star-rich disk make this explanation challenging. The flare would have to be orders of magnitude more powerful than any ever recorded from a typical star to be detectable across such a vast intergalactic distance. Another, more exotic possibility involves a neutron star. These dense remnants are capable of incredible radio outbursts. Perhaps this was a pulsar giant pulse, a rare event where a normally steady pulsar's lighthouse beam intensifies by a factor of thousands for just a few rotations. Alternatively, it could be a magnetar, a neutron star with an unimaginably powerful magnetic field experiencing a starquake on its rigid crust, releasing a torrent of radio energy. While these objects are more commonly associated with X-ray and gamma-ray flares, some are known to produce radio transients, and a magnetar wandering through the halo would be a prime candidate for such a bizarre and energetic signal. The frustrating and thrilling aspect of this discovery is its singular nature. Despite frantic and continuous follow-up observations of the same coordinates with the world's most sensitive radio dishes, the signal has never repeated. This non-detection is itself a critical piece of data. It rules out any periodic phenomenon like a regularly pulsing star or a binary system with predictable outbursts. The transient appears to have been a one-off event, a singular catastrophe or a unique alignment that we were fortunate enough to catch. This elevates the mystery, pushing theorists to consider even more speculative causes. Could it have been the final death scream of a star being torn apart by a rogue intermediate mass black hole? Or perhaps something entirely new, a class of radio phenomenon we haven't yet dreamed of? A flicker from an unknown engine operating in the deep dark between galaxies. The hunt for more of these events is now a major priority in radio astronomy. Each one is a potential clue to understanding the most energetic and poorly understood processes in the universe. This single, unconfirmed blip on a graph is a powerful reminder that for all our mapping and theorizing, the halo still holds onto its secrets, capable of surprising us with a sudden, brilliant, and enigmatic signal from the void. But our journey through Andromeda's halo now brings us to one of its most magnificent and massive structures, a glittering city of stars that stands apart from all others, the colossal globular cluster known as G1. In telescopic images, it is nothing short of breathtaking. While most globular clusters appear as dense, fuzzy balls of light, G1 reveals itself as an almost solid sphere of countless suns, a swarm so tightly packed and brilliant it can easily be mistaken for the core of a small galaxy. Its sheer size and luminosity set it apart immediately. It is the most massive globular cluster not just in Andromeda, but in our entire local group of galaxies, a true titan among its kind. Located roughly 130,000 light-years from Andromeda's center, it drifts through the halo like a sovereign world, a vast gravitational island unto itself. The true astonishment of G1, however, lies hidden at its very heart, a dark secret revealed not by optical light but by the precise motions of the stars swirling around it. For decades, astronomers have meticulously tracked the orbits of stars within the cluster's core, measuring their velocities with incredible precision. The stars closest to the center were moving far too quickly, zipping around as if caught in the grip of an invisible, monstrous gravity well. When scientists calculated the mass required to whip these stars around at such frantic speeds, the numbers were staggering. The only plausible explanation was the presence of a hidden anchor of immense proportions, a black hole. But this was no ordinary stellar mass black hole. The calculated mass was tens of thousands of times that of our Sun. This was compelling evidence for an intermediate mass black hole, a long-sought missing link in the black hole family, an object more massive than those formed from a single dying star, but far smaller than the supermassive beasts that dominate galactic centers. The implications of this discovery are profound. If confirmed, this intermediate mass black hole could be the key to solving one of astronomy's great puzzles: how supermassive black holes grow so enormous. One leading theory suggests they start as these intermediate seeds, forming in the dense environments of the earliest star clusters, and then growing over billions of years through mergers and accretion. G1, with its ancient age, could be preserving a pristine example of such a seed, a black hole fossil from the dawn of time, offering us a direct look at a potential building block of the universe's largest structures. Its presence also suggests a violent past for the cluster itself. It may not have formed as a single cluster, but could be the stripped nucleus of a dwarf galaxy that Andromeda consumed long ago, its stars scattered and its central black hole left as the glittering prize within this new massive cluster. Beyond its dark heart, G1 serves as the ultimate natural laboratory for studying the entire life cycle of a globular cluster. Its immense size and advanced age mean it has experienced every conceivable dynamical process. High-resolution images from the Hubble Space Telescope allow astronomers to study its stellar populations in exquisite detail, creating a color magnitude diagram that acts as a perfect evolutionary timeline for its stars. We can see the distinct turn-off point where stars are beginning to leave the main sequence, and the well-defined branches for red giants and white dwarfs, all telling a consistent story of a population that formed in a single, rapid burst over 12 billion years ago. The cluster's structure is also a record of its history. Its core is incredibly dense, a result of a process called core collapse, where gravitational interactions between stars over eons have caused the most massive ones to sink toward the center, creating a dazzlingly bright and crowded nucleus. Studying G1 is like having a detailed blueprint for how every massive cluster evolves. Its sheer gravity influences the fate of every star within it, fostering exotic objects like blue stragglers through stellar collisions and mass transfer in its crowded core. By understanding the intricate dynamics at play within this one magnificent cluster, we gain insights that apply to globular clusters throughout the universe. G1 is not merely an object in Andromeda's halo. It is a template, a standard against which all other clusters are measured, a microcosm of stellar evolution whose secrets help us decipher the story of how the most ancient structures in the cosmos live and die. While the Giant Stream is the most massive river of stars in Andromeda's halo, it is far from the only one. Our journey now brings us to another, more recently discovered stellar stream, a fainter but equally eloquent ribbon of stars that tells the story of a separate, more recent act of galactic cannibalism. This stream, often referred to by its catalog designation, but which we might call the Eastern Stream for clarity, is a crucial piece of the puzzle, helping astronomers piece together a detailed timeline of Andromeda's violent growth. Its discovery followed a now familiar pattern of digital sleuthing, emerging from the same deep photometric surveys that mapped the halo. Astronomers, using advanced computer algorithms, detected a statistically significant alignment of stars moving together through space, a faint but coherent flow that stood out against the random background of halo stars. This was the signature of another victim, a dwarf galaxy whose stars were now strung out along its final orbital path. Unraveling the story of this stream meant first trying to understand the properties of its progenitor, the original dwarf galaxy that was consumed. By studying the total luminosity of the stream and estimating how many stars have already dissolved into the wider halo, astronomers can reconstruct the original mass of the dwarf. The evidence suggests it was likely a small, run-of-the-mill dwarf spheroidal galaxy, not unlike many of the satellites still orbiting Andromeda today. Its stars, as revealed by spectroscopic analysis, are uniformly ancient and metal-poor, indicating it was a primitive system that formed early in the universe's history and experienced little subsequent star formation. This lack of complex chemistry makes it a relatively simple building block, a fundamental piece of galactic raw material that Andromeda incorporated into its structure. The true power of this stream, however, lies in its ability to act as a clock. The process of tidal disruption, the stretching of a galaxy into a stream, is not instantaneous. It happens over billions of years, and the precise length, width, and density of the stream we see today are direct products of how long ago the destruction began and the specific orbital path the dwarf galaxy followed. This is where sophisticated stream simulation videos become an indispensable tool for understanding. These are not mere artists' impressions. They are the output of powerful n-body computer simulations that model the laws of gravity acting upon millions of individual star particles. A typical simulation might begin by showing a small, coherent dwarf galaxy approaching the much larger disk of Andromeda. With each close pass, the simulation visualizes the immense tidal forces at work, stretching the smaller galaxy like cosmic taffy. We see stars being pulled from its leading and trailing edges, gradually populating an ever-lengthening arc that eventually forms a complete loop around the giant galaxy. By adjusting the initial conditions of the simulation, the dwarf galaxy's starting mass, its orbital speed, and its angle of approach, astronomers run countless iterations. The goal is to find the perfect match, a simulation whose final output, after billions of virtual years, perfectly mirrors the precise location, shape, and stellar density of the eastern stream we observe today. This painstaking process of matching simulation to observation allows scientists to do something remarkable. They can rewind the clock. The best fit simulation doesn't just show us how the disruption happened, it tells us precisely when it started. For this particular stream, the models indicate the dwarf galaxy began to be torn apart roughly 2 billion years ago, a relatively recent event in cosmic terms. This single data point is a crucial anchor in reconstructing Andromeda's accretion history. It shows that the galaxy's growth was not a single event that concluded long ago, but an ongoing process of accumulation that has continued across nearly the entire history of the universe. By dating multiple streams, astronomers can build a chronology of mergers, understanding how Andromeda's assembly rate has changed over time. Furthermore, the specific orbital path deduced from the simulation reveals the three-dimensional distribution of mass within Andromeda's dark matter halo. The stream's stars act as test particles, tracing the underlying gravitational potential. Any subtle kinks or wrinkles in the stream could indicate past interactions with other subhalos of dark matter, providing a unique probe of the invisible structure that makes up the majority of the galaxy's mass. This particular stream, therefore, is more than just the ghost of a single galaxy. It is a dynamic map and a historical record, its faint starlight illuminating not only a past cataclysm, but also the hidden architecture of the present-day galaxy it now calls home. But for all the violent dynamism and ancient starlight we have catalogued, some of the halo's most persistent mysteries refuse to be seen at all in visible light. They exist only as a whisper of warmth, a signature of heat radiating in the infrared part of the spectrum. This brings us to our next enigma, an unidentified infrared source, a brilliant beacon of thermal energy that, when astronomers point their most powerful optical telescopes at its precise coordinates, reveals absolutely nothing. It is a profound nothingness, a patch of empty black sky that somehow glows with intense heat. Its discovery was made by space-based infrared observatories like the Spitzer Space Telescope and more recently the James Webb Space Telescope, instruments designed to peer through cosmic dust and see the cold, hidden universe. The initial detection is a single, bright pixel in a vast infrared mosaic, a point of light that demands an explanation for its existence and its eerie optical silence. To understand why this is so puzzling, we need to step into the mind of an astronomer. When we find a bright point source in the sky, we expect it to be one of a few familiar things: a star, a distant quasar, a galaxy. These objects typically emit light across the electromagnetic spectrum. A star that is bright in the infrared, for instance, is often also visible as a red star to our eyes or in optical telescopes. This object breaks that fundamental rule. It is a stark disconnect, a powerful infrared source with no optical counterpart whatsoever. It's like feeling the heat of a roaring fire in a pitch-black room, your skin warming from the invisible flames, yet when you flip on the light switch, the room remains completely empty. Astronomers turn to a powerful diagnostic tool to begin their investigation, the infrared color diagram. Imagine a simple graph with two axes. The horizontal axis might plot the color difference between light detected at 3.5 and 4.6 microns, while the vertical axis represents the difference between 4.6 and 12 microns. Every known type of astronomical object has a favorite place to live on this graph. Cool, low-mass stars cluster in one region. Galaxies dominated by star formation sit in another. Objects shrouded in thick dust, like protostars, occupy a third zone. When the data points for this mysterious source are plotted, they don't fall neatly into any of these familiar categories. Its specific combination of infrared colors is unusual, pointing to a peculiar physical process or an extreme environment that we don't commonly encounter. This strange infrared fingerprint fuels several compelling theories. One leading idea is that we are looking at a dust-shrouded object right here in Andromeda's halo. This could be a unique type of star in a very late and extreme stage of its life, like a carbon star that has enveloped itself in an incredibly thick, opaque shell of freshly manufactured soot and dust. This cosmic cocoon would block all its visible light, but the star's heat would warm the surrounding dust, causing it to glow intensely in the infrared, turning the entire system into a brilliant infrared beacon hiding within a cloak of its own making. Alternatively, it could be a protoplanetary nebula, the brief transitional phase where a dying star has puffed off its outer layers, but its exposed core hasn't yet heated up enough to ionize the gas and make it glow visibly. For now, it is just a warm cloud of gas and dust, visible only to infrared eyes. Another fascinating possibility is that we are not looking at an object within the halo at all, but an incredible cosmic coincidence. The source could be a distant, extremely dusty galaxy located billions of light years behind Andromeda, seen directly through its halo. In the early universe, such galaxies were common, filled with dust from frantic star formation and glowing fiercely in the infrared. From our perspective, this faraway galaxy would be perfectly aligned with Andromeda's halo, its light reddened and dimmed by the vast cosmic distance, making it invisible to optical telescopes but still bright enough for our most sensitive infrared instruments to detect. We would be seeing a ghost from the cosmic dawn, its image projected onto the screen of our nearest galactic neighbor. The James Webb Space Telescope is the ultimate tool for solving this mystery. Its unparalleled infrared resolution and sensitivity allow it to do what Spitzer could not: peer into the heart of this infrared glow with breathtaking clarity. If the source is a single, dust-enshrouded star within the halo, JWST might be able to resolve its structure, perhaps detecting the faint asymmetry of a bipolar outflow or the subtle signature of specific molecules in its spectrum. If it is a background galaxy, JWST deep spectroscopic capabilities could measure its redshift, instantly confirming its immense distance and ruling out a local origin. Each piece of data narrows the possibilities, turning a single point of heat into a story about stellar death, galactic evolution, or the challenges of peering through a universe filled with overlapping secrets. This unidentified infrared source is a humbling reminder that for every question we answer about the halo, a new, more subtle mystery emerges from the warmth of the darkness. Amidst the halo's population of steady, ancient suns, one star behaves like a brilliant but erratic performer on a dimly lit stage, its light fluctuating in a bizarre and unpredictable dance. This variable star, catalogued with a long string of numbers and letters but which we might simply call V1, displays a pattern of brightening and dimming that defies easy classification, making it a fascinating puzzle for astronomers trying to understand the life cycles of stars in this unique environment. Its discovery wasn't about spotting a new point of light, but about noticing that an existing point of light refused to behave itself. By meticulously comparing photographic plates and later digital images taken over years and even decades, astronomers realized this particular star was anything but constant. Its irregular performance immediately set it apart from the vast majority of its halo neighbors, which burn with a steady, predictable intensity born from billions of years of stable fusion. To truly appreciate its strangeness, we need to look at its light curve, the fundamental graph that astronomers use to understand variable stars. Imagine a simple chart. The horizontal axis represents time, stretched out over weeks, months, or years. The vertical axis plots the star's brightness or magnitude. For a regular variable star like a Cepheid or an Ara Lyrae, this graph would show a beautiful, repeating wave-like pattern, as regular and predictable as a heartbeat. The light curve for V1 looks nothing like that. It's a chaotic scribble. The line lurches upward in a sharp, steep spike as the star rapidly brightens, holds for an unpredictable period, and then often plummets back down just as quickly. Other times, it might undergo a series of smaller, rapid flickers or enter a long period of relative calm before erupting again without warning. This complete lack of a discernible period is what makes it so enigmatic and so difficult to pin down. So what kind of stellar engine could produce such erratic behavior? Astronomers are investigating several compelling possibilities, each pointing to a different and dramatic physical process. One strong candidate is that V1 is a cataclysmic variable star. This isn't a single star, but a tightly bound binary system where a white dwarf, the Earth-sized core of a dead star, is locked in a gravitational tango with a living companion star, often a red giant. The white dwarf's immense gravity acts as a cosmic vampire, relentlessly pulling material, primarily hydrogen, from the outer layers of its donor star. This stolen gas doesn't fall directly onto the white dwarf. It spirals down, forming a hot, whirling accretion disk around it. Most of the time, this process is relatively steady, producing a low level of light. But occasionally, the conditions in the disk become unstable. When enough hydrogen accumulates on the surface of the incredibly dense white dwarf, the pressure and temperature can suddenly spike, triggering a runaway thermonuclear explosion. This is a nova outburst, a titanic stellar bomb that causes the entire system to brighten by a factor of 10,000 or more in just a few days, creating one of those dramatic spikes on the light curve before gradually fading as the ejected material dissipates. Another, more exotic possibility is that V1 is a symbiotic star, a specific and more extreme type of interacting binary. In this scenario, the companion to the white dwarf is a bloated, cool red giant. The transfer of material here is more complex, often involving a strong stellar wind from the giant that is captured by the white dwarf. These systems are known for their slow, irregular outbursts and their rich emission line spectra, which show evidence of both a very hot component and a very cool component, hence the name symbiotic. The outbursts are thought to be caused by instabilities in the accretion disk or by thermonuclear flashes on the white dwarf's surface, much like a nova but sometimes on a different scale. The combination of these two wildly different stars in a single system creates a perfect environment for the kind of complex and unpredictable variability we observe. The mere existence of such an object in the halo is itself a significant clue. Cataclysmic and symbiotic variable stars are typically associated with populations of younger stars, as they require a binary system to survive the mass transfer process over long periods. Finding one in the ancient halo suggests that binary systems were not only common in the early universe, but that they can remain stable and interact over truly cosmic timescales. By studying the specific characteristics of its light curve, the amplitude of its outbursts, the speed of its rises and declines, and the intervals between events, astronomers can work backwards to model the physics of the system. They can estimate the mass of the white dwarf, the rate of accretion, and the nature of the companion star, turning a single point of flickering light into a detailed laboratory for studying extreme stellar physics. This variable star is far more than a celestial curiosity. It is a dynamic probe. Its unpredictable flashes act like a strobe light, momentarily illuminating its immediate surroundings and allowing astronomers to perform spectroscopy during its outbursts, analyzing the composition of the ejected material. This material, enriched with elements forged in the nuclear fire of the explosion, gets recycled back into the halo, contributing to the chemical evolution of the galaxy in a small but measurable way. Each erratic pulse of light from V1 is a reminder that even in the quietest and most ancient neighborhoods of a galaxy, binary stars can engage in a dramatic gravitational ballet, their intimate and sometimes violent interactions writing a complex, flickering signature against the dark canvas of intergalactic space. The story of Andromeda's halo isn't just a tale of its past conquests. It's also a narrative of a long-term relationship with its largest and most significant companion, the Triangulum Galaxy, also known as Messier 33. This beautiful face on spiral is more than just a pretty neighbor. It is Andromeda's largest satellite, and evidence is mounting that their histories are deeply intertwined, marked by a dramatic close encounter that has left its mark on the very fabric of the halo itself. While they are now separated by nearly 700,000 light-years, their gravitational dance is far from over, a cosmic ballet that will eventually lead to another merger, reshaping both galaxies in the distant future. The clues for a past interaction are subtle but compelling, written in the motions of stars and the distribution of matter. The most telling evidence comes from a vast and tenuous bridge of hydrogen gas that appears to connect the two galaxies. This isn't a structure you can see in a typical telescope image. It's mapped through the faint 21-centimeter radio emission of neutral hydrogen atoms. This gaseous filament, stretching across the intergalactic void, acts like a cosmic umbilical cord, a relic from a time when the two galaxies passed close enough for their gravitational fields to pull material out into space, creating a tidal bridge between them. Furthermore, detailed observations of M33 itself reveal that its outer disk appears warped and distorted, a common signature of a strong gravitational encounter. It's as if the galaxy is still reeling from the gravitational pull of its massive neighbor, its structure permanently bent by the experience. Computer simulations are essential for recreating this ancient event. By inputting the current masses, positions, and velocities of Andromeda and Triangulum, astrophysicists can run the cosmic clock backwards and forwards to see what kind of interaction could have produced the structures we observe today. The most successful models suggest that rather than a direct head-on collision, M33 made a relatively close pass by Andromeda, perhaps 1 to 2 billion years ago. It wouldn't have needed to be an incredibly close shave. Even a pass within a few 100,000 light-years would have been sufficient for Andromeda's immense gravity to exert a powerful tidal force. This gravitational hand would have stretched M33, perturbing its disk and pulling a stream of gas out into intergalactic space, while also transferring energy and stirring up the outer reaches of Andromeda's own halo in the process. This past encounter helps explain some of the larger-scale structures and asymmetries we see in Andromeda's halo today. The gravitational shock of M33's passage would have sent ripples through the halo's population of stars and dark matter, much like a ship passing through water creates a wake. It could be responsible for triggering new star formation in certain isolated gas clouds, or for perturbing the orbits of existing globular clusters and dwarf galaxies, giving them an extra kick that sends them on more unusual paths. The halo is not a static museum exhibit. It's a dynamic record, and the interaction with Triangulum is a significant chapter in that history, an event that demonstrates how galaxies continually influence each other across vast distances. Looking forward, this gravitational tango is set to become far more intimate. While our own Milky Way is on a direct collision course with Andromeda, Triangulum is also part of this future cosmic real estate merger. Motion animations that plot the trajectories of all three galaxies reveal a complex three-body interaction. M33 is not just orbiting Andromeda, it is also falling towards it, caught in its gravitational well. Current predictions suggest that before the Milky Way even arrives on the scene, the Triangulum galaxy will likely be consumed by Andromeda. In roughly 2 billion years, it is expected to make a much closer approach, and this time the tidal forces will be too great for it to survive as an independent entity. It will likely be stretched and torn apart, its stars and gas eventually becoming another major stream in Andromeda's halo, a final grand addition to its collection of galactic debris. This future event will be a spectacular rerun of the dwarf galaxy mergers that built Andromeda in the first place, but on a much larger scale, a final act of galactic cannibalism that will leave Andromeda an even more massive and complex giant before it finally meets its own fate with our own galaxy. Drifting through the immense void of the halo, far from the ordered rotation of the galactic disk, is a cosmic nomad of pure potential, a massive, fast-moving cloud of primordial gas. This isn't a gentle wisp, it's a high-velocity cloud, a colossal structure of neutral hydrogen hurtling through the galactic hinterlands on a mysterious trajectory. Its movement is so rapid and distinct that it stands out dramatically against the more sedate background of the halo, a solitary wanderer with enough raw material to forge millions of new stars. Detecting this cloud required shifting our gaze away from the light of stars and tuning into the faint radio whispers of the universe. Radio telescopes, sensitive to the 21-centimeter wavelength emitted by neutral hydrogen atoms, act as our ears to this silent realm. They revealed not just the cloud's presence, but its intricate motion, painting a dynamic portrait of an object in a tremendous hurry. The origin story of this cloud is a subject of intense debate, with two compelling and opposing theories vying for explanation. The first is a tale of internal eruption, a galactic fountain. Imagine the furious energy at the heart of Andromeda's disk, where supernovae explode in violent succession, their collective force blasting enormous bubbles of hot gas high above the galactic plane. As this ejected material travels into the cooler halo, it condenses into massive clouds of neutral hydrogen that eventually reach a tipping point, succumbing to gravity and raining back down onto the disk in a cycle of cosmic precipitation. In this scenario, the high-velocity cloud is a returning droplet in this vast fountain, a piece of the galaxy that was violently expelled and is now completing its long fall back home, its high velocity a testament to the powerful gravitational pull it's experiencing. The second theory proposes an external, intergalactic origin. This cloud might not be a returning exile, but a first-time visitor, a pristine strand of the cosmic web finally falling into Andromeda's gravitational embrace after drifting for billions of years in the lonely void between galaxies. This would make it a late-arriving parcel of the same primordial hydrogen that first built the galaxy, a delayed delivery of cosmic building supplies that has never been enriched by the nuclear furnaces of previous stellar generations. Its composition holds the key to distinguishing between these stories. Spectroscopic analysis can search for the faintest traces of heavier elements, the astronomical term for any element beyond hydrogen and helium. If the cloud is completely metal-free, it points to an extragalactic origin. Even a minuscule sprinkling of heavier elements, however, would be the smoking gun, proving the gas was once part of the galactic disk, processed by stars and then ejected before now falling back. The true masterpiece of data that brings this cloud to life is its velocity field map. This isn't a simple image, it's a multi-dimensional chart that plots the cloud's movement in spectacular detail. Imagine a standard image of the cloud structure. Now, overlaid upon it is a vibrant color gradient, perhaps blue on one side, shifting to red on the other. This color scheme represents the Doppler shift, the change in the wavelength of the cloud's radio emissions caused by its motion relative to us. The blue shifted side is hurtling towards us, while the red shifted side is moving away. The map might reveal a complex pattern, showing not just a simple trajectory but internal motions, turbulence, rotation, or shear within the cloud itself. This detailed velocity structure allows astronomers to model its exact path, predicting whether it is on a direct collision course with the disk, destined to plunge into it and trigger a future burst of star formation, or if it will merely make a graceful arc through the halo and continue on its way. This single cloud is far more than an isolated curiosity. It is a critical component in the grand life cycle of a galaxy. Galaxies are not closed systems. They are dynamic engines that can bleed atmosphere and require fresh fuel to continue forming new stars. Over time, star formation locks up vast amounts of gas into stars, and supernova can eject material out of the disk entirely. Without a mechanism to replenish this lost fuel, a galaxy would eventually starve, its star formation sputtering out. High-velocity clouds are a key part of this recycling and accretion process. They represent both the return of processed material and the potential influx of brand new hydrogen, the essential fuel for future generations of stars. By studying its mass, velocity, and trajectory, we can calculate the rate at which Andromeda is currently gaining or recycling gas, providing a crucial data point for understanding its ongoing evolution and its capacity to light up with new stellar nurseries in the billions of years to come. Deep in the sparse stellar population of the halo, a star pulses with a rhythm so slow and deliberate it almost escapes notice, its light curve tracing a heartbeat that unfolds over years rather than days. This is the ultra-long period variable, a mysterious star whose very existence challenges our established classifications and forces us to reconsider the outer limits of stellar behavior. Its discovery wasn't the result of a single night's observation, but a triumph of long-term, patient dedication. Astronomers had to compare photographic plates and digital images spanning decades, meticulously measuring the brightness of countless faint halo stars to finally notice that one of them was undergoing a profound and incredibly gradual transformation. This wasn't the rapid flicker of a cataclysmic variable or the regular clockwork pulse of a Cepheid. This was a stellar giant breathing in slow motion, a luminous sigh in the cosmic dark. The defining characteristic of this star is written in its light curve, a graph that tells a story of immense scale and patience. Imagine a chart where the horizontal time axis is measured not in hours, but in hundreds or even thousands of days. The vertical brightness axis shows a smooth, wave-like pattern, but one so stretched out that a single cycle from minimum to maximum brightness and back again can take several years to complete. Placing this light curve beside that of a typical variable, like an Lyrae star with its frantic, day-long pulsations, creates a stunning visual contrast. It's the difference between a hummingbird's wing beat and the deep, tidal swell of an ocean. This incredibly long period is the first major clue that we are dealing with a star operating under a completely different set of physical rules. So what kind of star could pulsate on such an epic timescale? The leading theory points to the very largest and most luminous stars in the old halo population, ancient asymptotic giant branch stars, or GB stars for short. These are stellar behemoths in their final act, having exhausted the hydrogen and helium in their cores and now burning shells of fuel around an inert carbon-oxygen core. They are incredibly bloated, with radii that could engulf the orbit of Earth or even Mars. And herein lies the key to the mystery. The period of a star's pulsation is directly related to its size and density. Larger, less dense stars vibrate more slowly, just as a long, heavy pendulum swings with a slower, more deliberate rhythm than a short, light one. For a star to have a pulsation period of years, it must be of a truly colossal size, a supergiant even among giants. This presents a fascinating puzzle for stellar evolution models. These ultra-long period variables are found in the halo, an environment dominated by ancient metal-poor stars. Our models suggest that low metallicity stars actually evolved to become smaller and hotter at this stage of life compared to their metal-rich cousins. Finding such immense, pulsating giants there is therefore unexpected. It implies that our understanding of how a star's initial chemical composition affects its final structure and behavior is still incomplete. These stars might represent a rare and extreme evolutionary pathway, a brief but brilliant phase of instability that only a select few halo stars experience on their way to becoming white dwarfs. The implications of this discovery stretch far beyond mere classification. These slow, luminous pulsations make these stars incredibly powerful tools for cosmology. Their very long periods are exquisitely sensitive to their intrinsic luminosity. This means that by simply measuring the period of its pulsation, astronomers can determine the star's true brightness with remarkable accuracy. Once you know how bright a star truly is, comparing it to how bright it appears from Earth gives you its distance with incredible precision. This period luminosity relationship effectively turns each ultra-long period variable into a standard candle of extraordinary reach, capable of measuring distances far into the halo and even to other galaxies in our local group. They could become the next generation of cosmic yardsticks, helping us to map the three-dimensional structure of Andromeda's halo with unprecedented detail and refine our measurement of the expansion rate of the universe itself. Confirming this relationship and understanding the underlying physics requires an unwavering long-term commitment to observation. This is where century-long astronomical archives and dedicated monitoring programs become priceless. Visualizing this with a composite data graphic is powerful. Imagine a timeline stretching from the 1920s to the present day, with data points from historic glass photographic plates, early electronic sensors, and modern digital CCD cameras all plotted together to form a single, continuous, decades-long light curve. This incredible span of data is what allows astronomers to confidently trace the complete, years-long cycle of these stellar giants. Each new observation adds another point, further constraining the models and helping to unravel the unique conditions that drive such a profound and leisurely dance of light, a testament to the patient and cumulative nature of scientific discovery. And so our journey through the halo of Andromeda draws to a close, but the story it tells is far from over. From the colossal river of stars that is the giant stream to the faint, lingering glow of a mysterious infrared source, each of these 30 strange objects is a chapter in an epic narrative of creation and destruction. We've encountered the ghostly fingerprints of dark matter, the paradoxical youth of blue stragglers, and the lonely, high-velocity clusters racing toward escape. We've seen the stellar corpses of neutron stars and black holes, the dying breaths of planetary nebulae, and the ancient, fading embers of white dwarfs that serve as the galaxy's most reliable clocks. Each one, in its own unique way, contributes to a single, undeniable truth. Andromeda is not the serene spiral it appears to be from a distance. It is a cosmic predator, a galaxy built over billions of years through a relentless process of collision, cannibalization, and accretion. Its halo is not empty space. It is a dynamic archive, a sprawling graveyard, and a construction site all at once, holding the evidence of its violent past and the seeds of its future evolution. These discoveries do more than just satisfy our curiosity. They fundamentally reshape our understanding of how galaxies live and grow. The chaotic, lumpy structure of the halo, revealed in stunning detail by surveys like P&S, is the predicted signature of the hierarchical model of galaxy formation, a theory that states giants like Andromeda are built from the merging of countless smaller systems. Every stream, every overdensity, every rogue cluster is a direct observation that confirms this grand cosmic process. The sheer variety of these objects, from the incredibly metal-poor cluster EXT8 to the enigmatic radio transients, also reveals the incredible diversity of physical processes at work, from stellar dynamics and nuclear fusion to the still unknown nature of dark matter. They prove that the halo is a natural laboratory for extreme physics, offering us a chance to test our theories against the reality of the universe on its largest scales. Yet for every question answered, a dozen new mysteries emerge. The isolated clump of dark matter challenges our models of how this elusive substance should behave. The ultra-long period variable stars push the boundaries of our stellar evolution models. The faint, diffuse glow of gamma rays could be the signature of mundane cosmic ray interactions, or it could be the first direct hint of dark matter annihilation. These are not just minor puzzles, they are the frontiers of modern astrophysics, and Andromeda's halo is the perfect place to explore them. It is a reminder that our nearest galactic neighbor, for all we have learned, still holds profound secrets close to its chest. Now, we'd love to hear from you. After this tour of cosmic oddities, which of these 30 strange objects captured your imagination the most? Was it the doomed galaxy being shredded into the tidal tail of M110, the ancient, impossible cluster EXT8, or perhaps the haunting possibility of a rogue, intermediate mass black hole revealed only by a flicker of X-rays? Let us know your favorite in the comments below. We read every single one and love diving into these discussions with you. If you enjoyed this deep dive into the mysteries of our galactic neighbor, there's plenty more to explore. Our universe is filled with wonders, from the rings of Saturn to the hearts of distant quasars. Be sure to subscribe and hit the bell so you don't miss our next journey into the cosmos. Until next time, keep